2,500,000 light-years away from Earth, there is a huge galaxy spinning in the dark space full of stars, glowing with blue and golden colours that look like magic. We call it Andromeda, and it has more than 1 trillion suns inside it. When you look at this spiral galaxy, you are seeing light that travelled for millions of years until it reached our eyes. But here is the part that changes everything. Andromeda is moving in our direction right at this moment, travelling at more than 300 kilometers per second. This means that one day, billions of years from now, it will collide with our own galaxy, the Milky Way. Will life on Earth still exist when these two giant galaxies meet and dance together in space? Get ready to fall asleep while listening to this video and travel to this incredible place. Subscribe to the channel. Leave your like and comment from what part of the world you are watching. Get comfortable and relax. Let's begin. Looking up at the night sky, you might spot a faint smudge of light that doesn't quite look like a star. That misty patch represents the most distant object visible to the naked human eye, the Andromeda Galaxy. The story of how humanity came to understand this celestial neighbour is a fascinating journey spanning over 1,000 years. The first recorded observation of Andromeda dates back to 964 CE, when Persian astronomer Abd al-Rahman al-Sufi described it in his Book of Fixed Stars. He called it a little cloud and accurately charted its position in the night sky. This early observation is remarkable considering he had no telescope, just his eyes and meticulous attention to detail. For centuries, this mysterious patch of light remained just that, a curiosity noted by various astronomers but little understood. The European astronomical record of Andromeda begins much later, in the early 17th century. German astronomer Simon Marius provided the first detailed description in 1612, comparing its appearance to the light of a candle shining through horn. This poetic description gives us insight into how early astronomers struggled to characterize what they were seeing without understanding its true nature. The invention and refinement of the telescope gradually revealed more details about Andromeda, though its true identity remained elusive. Charles Messier, period, the famous French comet hunter, catalogued it in 1774 as the 31st object in his famous list of not comets, objects that might confuse comet seekers. This is why Andromeda is often referred to as Messier 31 or M31 by astronomers today. For centuries after these early observations, astronomers still believed Andromeda was part of our own Milky Way galaxy. The prevailing view of the universe at the time was that everything visible in the night sky existed within a single galaxy, our Milky Way. Andromeda and similar objects were thought to be spiral nebulae, clouds of gas, or star clusters within our galaxy. This understanding changed dramatically in the early 20th century. The Great Debate took place in 1920 between astronomers Harlow Shapley and Heber Curtis. Shapley argued that these spiral nebulae were part of our galaxy, while Curtis proposed they were separate island universes, what we now call galaxies, at tremendous distances from our own. The definitive answer came from Edwin Hubble in 1923. Using the 100-inch Hooker telescope at Mount Wilson Observatory, then the world's largest, Hubble observed individual stars within Andromeda. Among these stars were Cepheid variables, a special type of star whose brightness fluctuates in a predictable way related to its actual luminosity. This relationship, discovered by Henrietta Swan Leavitt years earlier, allowed Hubble to calculate the distance to these stars. What Hubble found was revolutionary. Andromeda was far beyond the boundaries of our Milky Way. His calculations showed it was approximately 900,000 light-years away. Modern measurements place it at about 2.5 million light-years. This conclusively proved that Andromeda was indeed a separate galaxy, a vast collection of stars, gas, and dust similar to our own Milky Way, but entirely distinct from it. This discovery fundamentally transformed our understanding of the universe. Suddenly, the cosmos expanded from a single galaxy to countless galaxies spread across an unimaginably vast space. Our cosmic perspective shifted dramatically, much like when humans first realized Earth was not the center of the solar system. Throughout the 20th century, increasingly powerful telescopes revealed more about Andromeda's structure. Astronomers identified its spiral arms, star clusters, and gas clouds. Radio telescopes detected hydrogen gas extending far beyond its visible boundaries. The launch of space telescopes in the late 20th century provided even clearer views, unhindered by Earth's atmosphere. The Hubble Space Telescope, launched in 1990, captured stunningly detailed images of Andromeda. These observations allowed astronomers to study individual stars and star clusters within the galaxy with unprecedented clarity. They revealed a complex structure with multiple spiral arms, a bright central bulge, and a population of globular clusters surrounding the galaxy. Modern observations have also revealed Andromeda's dynamic history. Evidence suggests it has consumed smaller galaxies throughout its lifetime, growing larger through these galactic mergers. Astronomers have identified stellar streams, remnants of these consumed galaxies, stretched around Andromeda like cosmic crime scenes. One of the most fascinating discoveries about Andromeda came in the early 21st century when astronomers confirmed that it is actually moving toward our Milky Way at approximately 110 kilometers per second. This means that in about 4.5 billion years, Andromeda and the Milky Way will collide and eventually merge into a single, larger galaxy. The historical journey of our understanding of Andromeda mirrors the advancement of astronomy itself. From naked-eye observations to space telescopes, each technological leap has revealed more about this neighbouring galaxy. The story begins with simple curiosity about a fuzzy patch of light and leads to profound realizations about the scale and nature of our universe. Today, amateur astronomers with modest equipment can observe Andromeda from their backyards, seeing roughly what Simon Marius described 4 centuries ago. Professional astronomers continue to study it with the most advanced instruments available, probing its composition, structure, and history. Andromeda remains one of the most studied objects in the night sky, a cosmic laboratory relatively close to home. The discovery of Andromeda as a separate galaxy represented one of the greatest expansions of human perspective in history. It took us from a universe consisting of a single galaxy to one containing billions of galaxies, fundamentally altering our cosmic understanding and our place within it. That faint smudge in the night sky, first noted over a millennium ago, continues to inspire wonder and discovery as we piece together the story of our cosmic neighbourhood. Physical characteristics of the spiral galaxy. When you gaze at the Andromeda galaxy through a telescope, you're looking at an island of stars so vast that light takes more than 100,000 years just to travel from one side to the other. This cosmic giant, officially designated as Messier 31, stands as the largest galaxy in our local group and offers astronomers a unique opportunity to study a spiral galaxy from the outside, something we cannot do with our own Milky Way. Andromeda spans an impressive area of the sky, covering an area more than 6 times the width of the full moon when including its faint outer regions. Despite this large apparent size, the galaxy's immense distance of approximately 2.5 million light-years means most of it is too faint for the naked eye to see. Only the bright central region appears as a fuzzy patch under dark skies. The overall structure of Andromeda follows what astronomers classify as a spiral galaxy with a distinct bulge and disk component. More specifically, it's considered a barred spiral galaxy, meaning it has a bar-shaped structure of stars crossing through its centre. This classification puts it in the same general category as our Milky Way, though with notable differences in size and arrangement. Andromeda's disk spans approximately 220,000 light-years in diameter, making it nearly twice the size of our Milky Way. This vast disk contains between 800 billion and 1.5 trillion stars, a stellar population potentially twice that of our home galaxy. These stars are arranged in a flattened disk with spiral arms winding outward from a bright central region. The spiral arms represent one of the most distinctive features of Andromeda. These massive structures curve gracefully around the galaxy, appearing as lighter bands against the darker background. Within these arms, the gas and dust are slightly more concentrated, leading to increased star formation. Young, bright blue stars trace these spiral patterns, making them stand out when observed in certain wavelengths. Unlike the Milky Way's relatively well-defined spiral structure, Andromeda's arms appear somewhat fragmented and complex, suggesting a history of interactions with neighbouring galaxies. At the centre of Andromeda lies a dense concentration of stars, forming what astronomers call the galactic bulge. This roughly spherical region extends about 15,000 light-years from the centre and contains predominantly older, redder stars packed more densely than in the galaxy's outer regions. The very core harbours a supermassive black hole designated as M31 star, with an estimated mass between 100 million and 240 million times that of our Sun, substantially larger than the Sagittarius A-star black hole at the centre of our Milky Way. Surrounding this bright central region is a feature known as Andromeda's ring structure. Observations have revealed a series of concentric rings or partial rings around the galaxy's centre, consisting of areas with enhanced star formation. Astronomers believe these rings may have formed due to interaction with satellite galaxies, sending waves of density through Andromeda's disk and triggering new star birth. Beyond the visible disk lies an enormous halo of stars extending more than 500,000 light-years from the centre. This sparsely populated region contains some of the galaxy's oldest stars, along with globular clusters, dense balls of hundreds of thousands of ancient stars that orbit the galaxy like tiny satellites. Andromeda possesses about 450 globular clusters, significantly more than the Milky Way's estimated 150 clusters. The visible stars and structures represent only a fraction of Andromeda's total mass. Like other galaxies, Andromeda is believed to be embedded in an enormous halo of dark matter, the mysterious substance that interacts through gravity but doesn't emit or absorb light. Scientists estimate that dark matter accounts for up to 90% of the galaxy's total mass, extending far beyond the visible boundaries and providing the gravitational force needed to hold the entire structure together. When examined across different wavelengths of the electromagnetic spectrum, Andromeda reveals different aspects of its composition and activity. In ultraviolet light, the galaxy highlights regions of active star formation where hot, young stars emit strongly. Infrared observations peer through the dust clouds to reveal hidden stellar nurseries and the overall distribution of older stars. X-ray observations show the locations of binary star systems containing black holes or neutron stars, as well as the hot gas surrounding the galaxy's central black hole. Radio wavelength observations have mapped Andromeda's neutral hydrogen gas, revealing a structure significantly larger than the visible galaxy. This gas serves as the raw material for future star formation, though Andromeda appears to be forming new stars at a slower rate than the Milky Way, approximately 1 solar mass per year compared to the Milky Way's rate of about 3 solar masses annually. Andromeda also contains substantial amounts of interstellar dust, tiny solid particles made primarily of carbon, silicon, and oxygen. This dust appears as dark lanes when silhouetted against the galaxy's bright background and plays a crucial role in the formation of new stars and planetary systems. The distribution of this dust follows the spiral pattern but shows particular concentration in a ring-like structure about 32,000 light-years from the centre. Studies of the stars in Andromeda have revealed details about its composition and history. The galaxy shows a gradient in metallicity, the proportion of elements heavier than hydrogen and helium, with stars in the central regions containing more heavy elements than those in the outer disk. This pattern suggests a long history of star formation and element enrichment, particularly in the denser central regions where multiple generations of stars have lived and died, each enriching the interstellar medium with heavier elements. Movement within the galaxy reveals additional complexity. Stars in the disk orbit the centre at speeds of hundreds of kilometers per second, while the overall rotation curve, the relationship between orbital speed and distance from the centre, provides some of the strongest evidence for dark matter's existence. Without this invisible mass, the outer regions of the galaxy would rotate much slower than observed. The immense physical structure of Andromeda that we see today represents billions of years of evolution, shaped by the force of gravity, the process of star formation, and likely interactions with neighbouring galaxies. As our nearest large galactic neighbour, it continues to serve as an invaluable cosmic laboratory, helping astronomers understand spiral galaxies throughout the universe. While the physical structure of Andromeda gives us insight into the nature of spiral galaxies, there's something even more fascinating to consider: the journey that every photon of light from Andromeda takes before reaching our telescopes and eyes. This cosmic voyage spans millions of years and represents one of the most remarkable aspects of astronomical observation. The light we currently observe from the Andromeda galaxy began its journey approximately 2.5 million years ago. To put this in perspective, when these photons began their travel toward Earth, our human ancestors were just beginning to craft stone tools, and species like Homo habilis were taking their first evolutionary steps. The entire span of human civilization, from the first agricultural settlements to our modern digital age, has unfolded during the time it took this light to cross the void between galaxies. Each photon begins its journey in a star, nuclear fusion reaction, or other energetic process within Andromeda. The photons generated in Andromeda's stars initially have to navigate through the galaxy itself. Some originate in the densely packed central bulge, where they might interact with numerous gas clouds and dust particles before escaping the galaxy's gravitational influence. Others come from the spiral arms or outer regions, facing fewer obstacles on their outward journey. After leaving Andromeda, these photons enter the vast intergalactic medium, the nearly empty space between galaxies. Here, the light travels through what might seem like absolute emptiness, but even intergalactic space contains approximately 1 atom per cubic meter on average, while incredibly sparse compared to anything we experience on Earth. Over millions of light years, these occasional atoms can interact with the travelling photons. During this intergalactic journey, the expansion of the universe itself affects the light. As space expands, it stretches the wavelength of light in a process called cosmological redshift. For Andromeda, this effect is quite small because it's relatively close on a cosmic scale, but it's still measurable with precise instruments. This redshift essentially means that the light arrives at a slightly lower energy and longer wavelength than when it departed. The journey through space isn't entirely uneventful. Intergalactic dust, while extremely thin, can absorb some wavelengths of light more than others, subtly altering the spectrum that eventually reaches Earth. Gravitational effects from other masses between Andromeda and Earth can also influence the path of light, sometimes acting as lenses that bend the trajectory of photons. As the light approaches our Milky Way galaxy, it encounters increasing amounts of gas and dust in our galactic halo before passing through the disk of our galaxy. Depending on which direction we're looking toward Andromeda, this light might pass through more or less material within our own galaxy, affecting how clearly we can see our neighbouring galaxy. The final leg of the journey brings these ancient photons through Earth's atmosphere, where they encounter yet another set of obstacles. Our atmosphere absorbs certain wavelengths entirely, particularly much of the ultraviolet and infrared spectrum. It also distorts and scatters light, creating the twinkling effect we see from stars and limiting the resolution of ground-based telescopes. This is why space telescopes like Hubble provide such remarkably clear images. They avoid atmospheric interference altogether. The photons that successfully complete this 2.5 million year journey might end their existence in the detectors of our telescopes or on especially dark nights away from city lights, directly in the retinas of human observers looking up at the night sky. Either way, these particles of light carry information across cosmic distances, serving as messengers from a different time and place. What makes this light journey particularly meaningful is that it gives us a perspective that transcends human timescales. When we observe Andromeda, we're seeing it as it existed millions of years ago, a form of natural time travel that lets us peer into the cosmic past. The galaxy we observe is fundamentally different from the one that exists now in an absolute sense, though this concept itself becomes complicated when dealing with the relativistic nature of time and space. The speed of light, approximately 300,000 kilometers per second, represents the ultimate cosmic speed limit according to Einstein's theory of relativity. Nothing can travel faster, which means that this 2.5 million year delay in receiving information from Andromeda is unavoidable. There's simply no way to know what Andromeda looks like right now in any meaningful sense. This same light travel effect applies to everything we observe in the universe, just on different timescales. Light from the moon takes about 1.25 seconds to reach Earth, from the sun about 8 minutes, and from the nearest star system, Alpha Centauri, Dot, about 4 years. The further we look out into space, the further back in time we're seeing. For astronomers studying Andromeda, this time delay presents both challenges and opportunities. It means we can never interact with Andromeda in real time, which would be relevant for any hypothetical communication. But it also gives us a valuable glimpse into the past of a galaxy very similar to our own, potentially offering insights into what the Milky Way might have looked like millions of years ago. The journey of light also reminds us of our place in the cosmos. Those photons began their journey long before modern humans existed and travelled through the emptiness of space while civilizations rose and fell on our planet. There's something profound about the fact that we've evolved the capacity to capture and understand this ancient light, using it to piece together the story of our cosmic neighbourhood. As we develop more advanced observational technologies, we continue to extract new information from this light. Different wavelengths reveal different aspects of Andromeda, from star-forming regions visible in ultraviolet light to the distribution of cold gas detected in radio waves. Each portion of the electromagnetic spectrum that reaches us adds another layer to our understanding of this neighbouring galaxy. The concept of light's journey emphasises the fundamental connection between time and space in astronomy. Distance isn't just measured in kilometres or light years, it's measured in time. When astronomers say Andromeda is 2.5 million light years away, they're simultaneously describing both how far and how long ago we're seeing it. This inseparable link between distance and time is one of the most fascinating aspects of observational astronomy. At the heart of the Andromeda galaxy lies one of the most enigmatic objects in the universe, a supermassive black hole that influences everything around it. This cosmic behemoth, officially designated as M31 star, written as M31 star by astronomers, similar to how our galaxy's central black hole is called Sagittarius A star, represents one of the most massive black holes in our local cosmic neighbourhood. Researchers estimate that Andromeda's central black hole contains between 100 million and 240 million times the mass of our Sun. To put this in perspective, it's approximately 50 to 100 times more massive than the black hole at the centre of our Milky Way. All of this mass is compressed into a region of space so small that it defies our everyday understanding of physics. The first evidence for this enormous object came from observations of the motion of stars in the galaxy's central region. Stars orbit the centre of Andromeda at tremendous speeds, hundreds of kilometres per second. According to Newtonian physics, objects moving this fast would escape the galaxy's gravitational pull unless they were being influenced by an extraordinarily massive, yet compact object. The only known cosmic structure that fits these requirements is a supermassive black hole. Direct observation of the black hole itself is impossible since black holes don't emit light. Instead, astronomers study its effects on surrounding matter and the radiation produced by material falling toward it. When gas, dust, or even stars venture too close to the black hole, they form what's called an accretion disk, a flattened spiral of material circling the black hole like water circling a drain. As this material accelerates and compresses, it heats up to millions of degrees, emitting energy across the electromagnetic spectrum, but particularly in X-rays. Chandra and XMM Newton, two space-based X-ray observatories, have captured images of the central region of Andromeda, revealing a source of X-rays consistent with material being heated as it falls toward the central black hole. However, these observations also revealed something surprising. Andromeda's central black hole is relatively quiet compared to many other galactic black holes. The term astronomers use for this is quiescent, meaning the black hole isn't actively consuming large amounts of material. It's essentially on a cosmic diet, accreting matter at a very low rate. This low activity level makes Andromeda's center much less luminous than so-called active galactic nuclei found in many distant galaxies, where black holes are consuming material at much higher rates and emitting tremendous amounts of radiation. This relative quietness raises interesting questions about Andromeda's history. Many astronomers believe that most supermassive black holes go through active and quiet phases throughout a galaxy's lifetime. The active phases often coincide with major galactic mergers that funnel large amounts of gas toward the center. The current quiescent state of Andromeda's black hole suggests it hasn't experienced a major influx of material in the recent astronomical past, though this could change in the future, particularly when Andromeda and the Milky Way begin their collision process. Surrounding the central black hole is a complex environment of stars, gas, and dust. Hubble Space Telescope observations have revealed a double nucleus structure, an unusual feature that puzzled astronomers for years. Further research showed that this isn't actually two separate nuclei, but rather a single cluster of stars orbiting the black hole in an eccentric, elongated pattern. This creates the appearance of two brightness peaks when viewed from Earth. The stars closest to Andromeda's central black hole live in an extreme environment. They orbit at tremendous speeds, experience intense gravitational forces, and are subject to high levels of radiation from other nearby stars and from material occasionally falling into the black hole. These conditions make the galactic center a natural laboratory for testing the predictions of general relativity and other physical theories under conditions impossible to replicate on Earth. The relationship between Andromeda's black hole and the galaxy as a whole reflects one of the most intriguing discoveries in modern astronomy: the tight correlation between the mass of a galaxy's central black hole and the properties of the galaxy itself, particularly the velocity dispersion of stars in the central bulge. This relationship, found across many galaxies, suggests that the evolution of galaxies and their central black holes are intimately connected, though the exact nature of this connection remains an active area of research. How did Andromeda's central black hole reach such an enormous size? Current theories suggest that supermassive black holes grow through two main processes. The first is by accreting gas, dust, and stars over billions of years, essentially eating their way to larger masses. The second growth mechanism occurs when black holes merge during galaxy collisions. When two galaxies containing central black holes combine, their black holes will eventually find each other and merge into an even larger black hole. Evidence from Andromeda's structure suggests it has absorbed several smaller galaxies throughout its history, and these events likely contributed to the growth of its central black hole. The current size of M31 star represents the cumulative result of billions of years of accretion and mergers. In the far future, when Andromeda and the Milky Way collide, their respective supermassive black holes will eventually merge as well. This cosmic collision, predicted to occur billions of years from now, will create an even more massive black hole at the heart of the resulting galaxy, before the final merger. The two black holes will likely form a binary system, orbiting each other in an elaborate gravitational dance that could last millions of years. When supermassive black holes finally merge, they release enormous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time itself. While current gravitational wave detectors aren't sensitive enough to detect the early stages of this process, future space-based observatories may be able to observe the gravitational wave background created by distant black hole mergers throughout the universe. The central black hole of Andromeda, while impossible to see directly, leaves its mark on everything around it. It has helped shape the evolution of the entire galaxy, influenced the motion of billions of stars, and will play a crucial role in the future when our two galaxies become one. Despite being one of the most extreme objects in physics, with properties that seem to defy common sense, it follows the elegant mathematics of Einstein's general relativity with perfect precision. The central black hole of Andromeda represents just one element of this massive galaxy that's actually on a collision course with our own. While the supermassive black holes from both galaxies will eventually merge in the distant future, the entire process of galactic collision warrants closer examination. This cosmic dance between Andromeda and the Milky Way will fundamentally transform our galactic neighborhood in ways that are both catastrophic and creative. The first concrete evidence that Andromeda is moving toward us came in the early 20th century when astronomers measured its radial velocity, the speed at which an object moves directly toward or away from an observer. While most galaxies in the universe are moving away from us due to cosmic expansion, Andromeda stands as a notable exception. It's approaching our galaxy at approximately 110 kilometers per second, fast enough to cover the distance from Earth to the Moon in just under an hour. Despite this seemingly rapid approach, the vast distance between our galaxies means the collision won't begin for about 4.5 billion years. When it does start, it won't be a simple head-on crash. Computer simulations show that the initial encounter will likely be more of a glancing blow, with the two galaxies passing by each other before gravity pulls them back for additional encounters. The entire collision process will unfold over billions of years. After the first approach, both galaxies will be severely distorted by each other's gravitational fields. The elegant spiral structures will be disrupted as stars are pulled into long streams and arcs. The galaxies will move apart again before gravity brings them back for a second, closer pass, perhaps a billion years after the initial encounter. With each successive pass, the two galaxies will lose energy through gravitational interactions and friction from gas clouds colliding. This will cause them to settle closer together until they finally merge completely, a process that may take up to 6 billion years from the initial approach. The end result will be a single, larger galaxy that astronomers have playfully nicknamed Milkomeda or Lactomeda. This future combined galaxy will likely be elliptical rather than spiral in shape. Elliptical galaxies are more three-dimensional and lack the distinctive disk and spiral arm structures of galaxies like the present-day Milky Way and Andromeda. They typically contain older stars and have less ongoing star formation, as much of the gas that would form new stars is either consumed in an initial burst of star formation during the merger or dispersed into intergalactic space. One of the most surprising aspects of galactic collisions is that despite the countless stars involved, over 1 trillion between both galaxies, direct collisions between individual stars will be extremely rare. This is because stars are incredibly small relative to the distances between them, even in the densest regions of both galaxies. Stars are typically separated by distances millions of times greater than their diameters. The odds of two stars directly colliding during the merger are similar to the odds of two mosquitoes colliding if each was flying randomly within the entire volume of Earth's atmosphere. While stars themselves rarely collide, the gas and dust distributed throughout both galaxies will interact much more directly. When clouds of gas collide, they compress, creating perfect conditions for the formation of new stars. This means the collision will likely trigger an enormous burst of star formation, particularly during the closest approaches of the two galaxies. Some models suggest the merger could create billions of new stars, briefly increasing the star formation rate by a factor of 10 or more compared to the current levels in either galaxy. The fate of our own solar system during this cosmic collision depends largely on its position within the Milky Way at the time. Currently, the Sun orbits about 26,000 light-years from the galactic center, roughly halfway out in the galactic disk. Computer models suggest that stars at this distance have a good chance of being flung into a more extended orbit around the newly forming elliptical galaxy. There's a smaller but still significant chance the Sun could be thrown into a more central region or even ejected into intergalactic space, though the latter outcome is considered unlikely. Even if the solar system remains in a stable orbit, the night sky as seen from Earth, if Earth still exists and harbours observers, would change dramatically. The familiar band of the Milky Way would gradually disappear as the galactic disk is disrupted. In its place would be a spectacular view of Andromeda filling much of the sky as it approaches, followed by chaotic streams of stars during the merger process, and eventually a more uniform distribution of stars in all directions once the elliptical galaxy forms. It's worth noting that by the time this collision begins, the Sun will have already evolved significantly. In 4.5 billion years, the Sun will be nearing the end of its main sequence life, becoming brighter and larger as it begins to exhaust its hydrogen fuel. By the final stages of the galactic merger, the Sun will likely have become a red giant, potentially engulfing the inner planets including Earth. This means that any observers of the complete merger would need to be either post-human species that have migrated elsewhere or civilizations from other star systems. The collision between Andromeda and the Milky Way won't be unique in cosmic history. Galaxy mergers have been common throughout the universe's evolution and have played a crucial role in building larger structures. Many of the most massive galaxies we observe today are thought to be the products of multiple mergers. Both Andromeda and the Milky Way show evidence of having absorbed smaller galaxies in the past, and the upcoming collision represents a continuation of this galaxy-building process, just on a larger scale than either galaxy has experienced recently. As these two spiral giants draw closer over the coming billions of years, they will gradually transform our local corner of the universe. From two distinct spiral galaxies with active star formation and clear structural features, they will create a single, massive elliptical galaxy, larger, redder, and less active than either of its progenitors, but containing the combined stellar populations of both galaxies and the new stars born during the merger itself. While the collision of Andromeda and the Milky Way represents a future we can predict but never personally witness, the idea of reaching Andromeda through space travel captures the imagination. The technological challenges of such a journey are immense, far beyond our current capabilities, but they offer a fascinating glimpse into the limits of what might someday be possible. The most fundamental obstacle to reaching Andromeda is the staggering distance involved. At 2.5 million light-years away, a spacecraft travelling at the speed of our fastest current probes would take tens of billions of years to reach Andromeda, many times longer than the current age of the universe. The Voyager spacecraft, for example, travel at approximately 17 kilometers per second relative to the Sun. At this speed, a journey to Andromeda would take over 42 billion years. Even our most advanced theoretical propulsion systems fall far short of making such a journey practical. Chemical rockets, which power all current human space exploration, are limited by the amount of fuel they can carry and the energy released by chemical reactions. These limitations make them entirely unsuitable for intergalactic travel. More advanced concepts like nuclear propulsion offer significant improvements but still fall short of the necessary capabilities. Nuclear fission or fusion rockets could potentially achieve speeds of perhaps 5 to 10% of the speed of light, even at these vastly improved velocities. the journey to Andromeda would still take between 25 and 50 million years, timeframes incompatible with human lifespans or even the duration of human civilization thus far. Some speculative propulsion concepts push the boundaries further. Antimatter engines, which would harness the energy released when matter and antimatter annihilate each other, could theoretically achieve speeds approaching 50% of light speed. This would reduce the travel time to only 5 million years, still far beyond practical consideration for a human mission. Breakthrough Starshot. A current research project proposes using powerful ground-based lasers to accelerate tiny spacecraft to 20% of light speed for interstellar exploration. Even if this technology could be scaled up dramatically, the travel time to Andromeda would still be measured in millions of years. Beyond propulsion, any mission to Andromeda would face numerous additional challenges. The spacecraft would need to navigate the intergalactic medium for millions of years, avoiding damage from interstellar dust and radiation. Each dust particle, though tiny, would impact with tremendous energy due to the high relative velocity, potentially causing significant damage over time. Power generation represents another major hurdle. Nuclear power sources used on current deep space missions typically provide reliable energy for a few decades. Even advanced nuclear isotope batteries would decay long before reaching Andromeda. Solar power becomes useless beyond our solar system as the sun's light dims with distance. Any practical intergalactic spacecraft would need a power source that could function reliably for millions of years, something far beyond our current technology. Communication across intergalactic distances introduces another layer of complexity. Radio signals weaken with the square of distance, meaning communications from Andromeda would be billions of times weaker than those from the edge of our solar system, even with enormous transmitters and receivers. The 2.5 million year delay for signals to travel each way would make any form of dialogue impossible. Any mission to Andromeda would essentially be on its own, unable to receive meaningful mission updates or instructions from Earth. The human element presents perhaps the most profound challenge. No existing life support system could sustain humans for the millions of years required for such a journey. This has led to several theoretical approaches to the problem of long-duration space travel. Generation ships represent one concept, where multiple generations of humans would live and die aboard the spacecraft, with only distant descendants reaching the destination. However, maintaining a stable, self-sufficient human population with enough genetic diversity would require thousands of individuals and enormous resources. The social and psychological challenges of maintaining a society in isolation for millions of years seem insurmountable. Suspended animation or human hibernation offers another theoretical approach, allowing travelers to skip the journey time. However, current cryogenic preservation techniques cannot safely preserve and revive living humans. Even if such technology were perfected, maintaining cryogenic systems reliably for millions of years presents its own immense challenges. Mind uploading represents an even more speculative possibility, where human consciousness might be transferred to digital substrates that could endure the journey timeframes. Such technology remains firmly in the realm of science fiction, with fundamental questions about consciousness and identity still unanswered. Robotic missions avoid some of these human-centric problems, but introduce others. Building electronic systems that could function reliably for millions of years would require breakthroughs in materials science and redundant engineering far beyond current capabilities. Even the most advanced artificial intelligence systems would need to operate autonomously for timeframes millions of times longer than any current technology. The most speculative technologies for intergalactic travel involve shortcuts through space-time itself. Theoretical constructs like wormholes or Alcubierre drives, often called warp drives, could potentially allow faster-than-light travel without violating Einstein's special relativity, which prohibits matter from accelerating past light speed through normal space. However, these concepts require exotic matter with negative energy density or other physical properties that may not exist in reality. even if physically possible. The engineering challenges of creating stable wormholes or warping space-time around a spacecraft would be beyond anything humanity has ever attempted. When considering a journey to Andromeda, we ultimately face the humbling reality that some voyages may remain forever beyond human reach, not just due to current technological limitations, but because of fundamental physical constraints. The vast intergalactic distances that light itself takes millions of years to cross serve as a powerful reminder of the scale of our universe and the limits of human exploration, at least as we currently understand physics and technology. While intergalactic travel remains beyond our technological horizon, we can still deepen our understanding of the Andromeda Galaxy through careful observation of its entire galactic system, just as our Milky Way is surrounded by smaller companion galaxies. Andromeda doesn't exist in isolation, but dominates a complex system of satellite galaxies that orbit around it, collectively forming what astronomers sometimes call a mini-local group within our larger galactic neighborhood. Andromeda currently hosts approximately 30 known satellite galaxies of various sizes and shapes. These smaller galaxies are gravitationally bound to their massive parent, orbiting Andromeda much as the Moon orbits Earth, though on vastly larger scales and longer timeframes. The most prominent of these satellites are visible even through modest amateur telescopes, Messier 32, M32, and Messier 110, M110, both discovered by Charles Messier in the 18th century. M32 is particularly distinctive as it appears very close to Andromeda's core in our line of sight. This compact elliptical galaxy is relatively small, spanning only about 2,000 light-years in diameter, but it contains several billion stars packed into a dense, bright concentration. Its appearance is somewhat unusual for a satellite galaxy, leading astronomers to develop an interesting theory about its formation. Evidence suggests M32 may once have been a larger spiral galaxy that was stripped of its outer regions through gravitational interactions with Andromeda. This process, called tidal stripping, effectively peeled away the outer stars and gas, leaving behind only the dense central core that we observe today. The other prominent satellite, M110 DOT, presents a stark contrast to M32. This elliptical galaxy is larger and more diffuse, with a diameter of approximately 15,000 light-years. Unlike the compact M32, M110 exhibits a more stretched-out structure with less clearly defined boundaries. Observations have revealed ongoing star formation within M110, unusual for elliptical galaxies which typically contain older stellar populations with little new star birth. Beyond these two prominent companions, Andromeda's satellite system includes numerous dwarf galaxies, much smaller and fainter than M32 or M110. These dwarf galaxies fall into several categories based on their structure and stellar content. Dwarf ellipticals have smooth, rounded appearances. Dwarf spheroidals are extremely low in density, with relatively few stars spread over a large volume. And dwarf irregulars show chaotic structures with ongoing star formation. One particularly interesting member of Andromeda's satellite family is Andromeda 19, discovered in 2008. This dwarf spheroidal galaxy is extremely diffuse, with its stars spread over an area similar in size to the full moon as seen from Earth. Despite this large apparent size, it contains relatively few stars, making it one of the lowest density galaxies ever discovered. Galaxies like Andromeda 19 challenge our understanding of how such diffuse structures can remain intact against the tidal forces exerted by their massive parent galaxy. The distribution of these satellite galaxies around Andromeda has become a subject of intense astronomical interest. Observations suggest many of Andromeda's satellites lie in a thin, disk-like plane around the main galaxy, rather than being randomly distributed in all directions, as simple models might predict. This unexpected arrangement, also observed around our Milky Way, has been termed the satellite plane problem and presents a challenge to current models of galaxy formation. Some astronomers suggest this planar arrangement might result from satellites that formed together from filaments of dark matter and gas, while others propose they might be remnants of past galactic collisions. The satellite galaxies of Andromeda provide valuable insights into the process of galactic evolution and the role of environment in shaping galaxies. Many show signs of interaction with Andromeda itself, distorted shapes, trails of stars pulled away by gravitational forces, or truncated star formation suggesting their gas has been stripped away. These interactions demonstrate the hierarchical nature of galaxy formation, where larger galaxies grow partly by consuming smaller ones. This process of galactic cannibalism is evident in the streams of stars found around Andromeda. These stellar streams are the remnants of satellite galaxies that ventured too close to Andromeda and were torn apart by its immense gravitational forces. The giant stellar stream, discovered in 2001, extends over 400,000 light-years and contains the shredded remains of at least one dwarf galaxy that was disrupted perhaps 1 billion years ago. By studying these streams, astronomers can reconstruct the orbital histories of destroyed satellites and better understand Andromeda's growth over cosmic time. The interaction between Andromeda and its satellites offers a preview of what awaits our own Milky Way and its companions. Before the Milky Way and Andromeda collide, many of these smaller galaxies will have already merged with their parent galaxies. Others may be flung into new orbits by the gravitational perturbations of the approaching galaxies, while some might become trapped in complex orbits around both major galaxies during the early stages of their interaction. Together, Andromeda, the Milky Way, their respective satellite systems, and other nearby galaxies form what astronomers call the local group, our immediate galactic neighbourhood spanning about 10 million light-years in diameter. Within this local group, Andromeda and the Milky Way are the dominant members, each commanding their own mini-systems of satellites. The third largest member, the Triangulum Galaxy, M33, is itself possibly a satellite of Andromeda, though its status is debated. Some evidence suggests Triangulum may have had a close encounter with Andromeda in the past and could eventually be absorbed by it before the Andromeda-Milky Way collision occurs. The satellite galaxies and stellar streams around Andromeda serve as a crucial laboratory for testing theories of galaxy formation and dark matter distribution. Their movements reveal the gravitational influence of dark matter extending far beyond Andromeda's visible boundaries. By carefully mapping the velocities of these satellites, astronomers can trace the distribution of dark matter and test whether it conforms to predictions from cosmological models. Studying Andromeda's satellites also gives us perspective on our own galactic neighbourhood, the Milky Way's satellites, including the large and small Magellanic Clouds visible from the southern hemisphere, represent a similar system to what we observe around Andromeda. By comparing these two satellite systems, astronomers can determine which features are common to large spiral galaxies and which might be unique to either Andromeda or the Milky Way. As astronomical instrumentation continues to improve, we discover ever fainter and more distant members of Andromeda's satellite family. Each new discovery adds another piece to the puzzle of how galaxy groups form and evolve over cosmic time. These satellite galaxies, though small by cosmic standards, contain millions or billions of stars, each potentially hosting planetary systems. They remind us that even within our local cosmic neighbourhood, there exists an incredible diversity of environments where stars shine and planets may orbit. Our ability to study Andromeda and its satellite system in such detail relies entirely on the remarkable advances in observational astronomy over the past century. From the humble beginnings of visual observations through small telescopes, our methods for examining this neighbouring galaxy have evolved dramatically, enabling us to probe Andromeda across the entire electromagnetic spectrum and reveal details that were completely inaccessible to earlier generations of astronomers. Modern observations of Andromeda employ an impressive array of ground-based and space-based instruments, each providing unique perspectives on different aspects of the galaxy. Large optical telescopes like the 8.2-meter Subaru telescope in Hawaii or the 10-meter Keck Observatory can resolve individual bright stars in Andromeda, allowing astronomers to study stellar populations and determine their ages, compositions, and motions. These telescopes use advanced imaging techniques and spectrographs to split light into its component wavelengths, revealing detailed information about chemical composition and velocity. Perhaps no instrument has revolutionized our view of Andromeda more than the Hubble Space Telescope. Since its launch in 1990, Hubble has captured stunning high-resolution images that reveal Andromeda's structure in unprecedented detail. The Panchromatic Hubble Andromeda Treasury Project, PHAT, completed in 2013, represents one of the most ambitious surveys ever conducted with Hubble. This multi-year program observed over 100 million individual stars in a large portion of Andromeda's disk, creating the most detailed portrait ever made of a spiral galaxy beyond our own. The power of Hubble's observations lies not just in their visual clarity, but in the scientific data they provide. By identifying different types of stars, from blue supergiants to red giants, astronomers can map out regions of recent star formation versus areas dominated by older stellar populations. Variable stars like Cephids, which brighten and dim in a predictable pattern related to their intrinsic luminosity, allow precise distance measurements that have helped refine our understanding of Andromeda's position in space. While optical telescopes reveal the visible structure of Andromeda, other wavelengths of light uncover completely different aspects of the galaxy. Radio telescopes like the Very Large Array in New Mexico or the Atacama Large Millimeter Array in Chile detect the cold hydrogen gas and molecular clouds that serve as the raw material for star formation. These observations show that Andromeda contains vast reservoirs of gas arranged in complex structures, including rings and spiral arms. Though, interestingly, its current rate of star formation is lower than might be expected given this abundant supply of raw materials. At the opposite end of the electromagnetic spectrum, space-based X-ray observatories like NASA's Chandra and ESA's XMM Newton detect the most energetic phenomena in Andromeda. These include X-rays emitted from binary star systems where matter falls onto neutron stars or black holes, as well as the remains of supernova explosions where shockwaves heat gas to millions of degrees. The distribution of these X-ray sources provides information about Andromeda's population of compact objects and its history of stellar deaths. Infrared observations, meanwhile, cut through the obscuring dust that blocks visible light and reveals the galaxy's overall structure of older stars and dust lanes. The Spitzer Space Telescope, and more recently the James Webb Space Telescope, can detect the heat radiation from cool stars and dust clouds, highlighting regions where stars are currently forming behind veils of dust invisible to optical telescopes. These infrared observations show that Andromeda's star formation is concentrated in a series of rings, including a prominent ring about 30,000 light-years from the galaxy's center. Ultraviolet telescopes like NASA's GALEX, Galaxy Evolution Explorer, reveal the youngest, hottest stars in Andromeda, massive, short-lived giants that emit strongly in ultraviolet wavelengths. The distribution of these ultraviolet bright stars traces the most recent episodes of star formation and helps astronomers calculate how quickly new stars are being born throughout different regions of the galaxy. Beyond simply observing across different wavelengths, modern astronomical techniques include specialized approaches that extract even more information. Spectroscopy, splitting light into its component wavelengths, reveals not just what elements are present in Andromeda's stars and gas clouds, but also how fast they're moving toward or away from us. This allows astronomers to map the rotation of the galaxy and measure the velocities of individual stars and gas clouds. Polarimetry, measuring the polarization of light, helps map magnetic fields within Andromeda by detecting how dust grains align with these fields. Photometry, precisely measuring the brightness of objects, allows astronomers to determine the ages and masses of star clusters by comparing their colours and luminosities with theoretical models of stellar evolution. Time domain astronomy, observing how objects change over time, has become increasingly important for studying Andromeda. Regular monitoring programs detect transient phenomena like supernova explosions, allowing rapid follow-up observations with multiple telescopes over longer timescales. Repeated observations can track the orbits of stars around Andromeda's centre or the proper motions of its satellite galaxies. The digital revolution has transformed how we process and analyse observations of Andromeda. Modern astronomical data often consists of terabytes of information that requires sophisticated computational techniques to analyse. Machine learning algorithms help identify patterns in this data, from automatically classifying different types of stars to detecting subtle structures in the galaxy's outer regions that might indicate past merger events. Computer simulations complement these observations by allowing astronomers to model Andromeda's evolution over billions of years. By comparing simulated galaxies with real observations, researchers can test theories about how Andromeda formed and evolved to its present state. These simulations have become increasingly sophisticated, incorporating everything from the effects of supernova explosions on surrounding gas to the gravitational influence of dark matter on the galaxy's overall structure. The combined power of these diverse observational methods provides a comprehensive view of Andromeda that would have been unimaginable to earlier generations of astronomers. From its central supermassive black hole to the faintest dwarf satellite galaxies on its periphery. From newly forming stars to ancient globular clusters, we can now study Andromeda in remarkable detail, despite its vast distance from Earth. These observations not only tell us about our galactic neighbour, but provide crucial insights into galaxy evolution throughout the universe. The remarkable observational tools we use to study Andromeda today give us a snapshot of the galaxy as it currently exists. However, like all galaxies, Andromeda has undergone a long and complex evolution to reach its present state. By analysing the structure, motion, and composition of its stars, gas, and dust, astronomers can piece together the historical timeline of how this massive spiral galaxy formed and evolved over billions of years. Andromeda began taking shape approximately 10 billion years ago, emerging from the primordial gas that pervaded the early universe. After the Big Bang, the universe consisted primarily of hydrogen and helium gas distributed almost, but not quite, uniformly through space. Tiny density fluctuations, imprinted in the earliest moments of the universe and amplified by gravity over time, caused some regions to become slightly denser than others. These denser regions attracted more matter, growing increasingly massive and eventually collapsing under their own gravity to form the first galactic structures. The earliest incarnation of what would become Andromeda likely didn't resemble the majestic spiral we see today. Computer simulations of galaxy formation suggest that the first galaxies were relatively small, irregular collections of stars and gas. The modern Andromeda galaxy grew through a combination of two main processes: the steady accretion of gas from the intergalactic medium and a series of mergers with other, smaller galaxies. Evidence for this merger-rich history is written across Andromeda's structure. The giant stellar stream, mentioned earlier, represents the remains of at least one small galaxy that was torn apart and is currently being incorporated into Andromeda. Other telltale signs include shells and ripples in the galaxy's outer regions, features that can only form when smaller galaxies are disrupted by the gravitational pull of a larger one. Detailed studies of the stars in different parts of Andromeda reveal a complex portrait of galactic aging. In the central bulge, astronomers find predominantly old, red stars with relatively high metallicity, astronomer speak for elements heavier than hydrogen and helium. These heavy elements could only have been created inside earlier generations of stars that exploded as supernovae, scattering these newly forged elements into space to be incorporated into newer stars. The high metallicity of bulge stars indicates they formed later in cosmic history, after several generations of stars had already lived and died, enriching the interstellar medium with their stellar alchemy. In contrast, the halo surrounding Andromeda contains many ancient, low metallicity stars, some perhaps nearly as old as the universe itself. These stars formed when the galaxy was young and the interstellar medium had experienced little enrichment from previous stellar generations. By mapping the distribution of stars with different ages and chemical compositions, astronomers can reconstruct the sequence of star formation throughout Andromeda's history. The most dramatic evidence for Andromeda's turbulent formation history may be hidden in plain sight: its basic spiral structure. While spiral arms might seem like permanent features, they're actually dynamic patterns that have evolved over billions of years. The distinctive spiral structure we see today likely didn't exist in Andromeda's youth. Instead, it developed gradually through the interactions of stars and gas clouds orbiting at different speeds, and possibly through gravitational perturbations from passing satellite galaxies. The prominent bar structure crossing through Andromeda's centre represents another relatively recent development. Bars form when stellar orbits become aligned due to gravitational interactions, creating an elongated structure that rotates like a solid object within the galaxy. Simulations suggest bars often develop after galaxies have already established their disk structure, perhaps a few billion years into their evolution. The presence of this bar indicates Andromeda's structure has continued to evolve even after its basic spiral pattern was established. By examining different regions of Andromeda, astronomers can read the galaxy's history like geological layers on Earth. The central regions contain the oldest average stellar populations, while the disk shows a mix of stellar ages indicating ongoing star formation over billions of years. The spiral arms contain the youngest stellar populations, highlighting regions where star formation continues in the present epoch. Over its lifetime, Andromeda has experienced several major episodes of star formation. These can be identified by looking at clusters of stars that formed at approximately the same time. Evidence suggests that about 4 to 8 billion years ago, Andromeda experienced a significant increase in star formation, possibly triggered by a major merger event or interaction with another galaxy. This period of enhanced starbirth would have temporarily transformed Andromeda into what astronomers call a starburst galaxy, with dramatically increased luminosity from the light of newly formed massive stars. More recently, the rate of star formation in Andromeda has declined to about 1 solar mass per year, lower than the rate in our own Milky Way. This reduced star formation rate, combined with the prominent bulge and relatively small gas fraction compared to other spiral galaxies, suggests Andromeda may be in a more advanced stage of galactic evolution than our own galaxy. It has converted a greater proportion of its gas into stars and is gradually transitioning toward becoming a more quiescent system. The presence of rings of star formation in Andromeda, rather than continuous spiral arms of star formation, may represent another sign of this maturing process. These rings could have been created by density waves moving through the galactic disk, or possibly by the gravitational effects of satellite galaxies passing close to Andromeda. The outermost ring of star formation may have been triggered by an interaction with the Triangulum galaxy, M33, a few billion years ago. As astronomers continue to piece together Andromeda's history, they're developing a narrative that spans almost the entire age of the universe. From its humble beginnings as a condensation in the cosmic web of dark matter and gas, through a series of mergers and interactions that built it into the massive galaxy we see today. Andromeda's evolution reflects the basic processes that have shaped galaxies throughout cosmic history. Its future, a collision and merger with our own Milky Way, represents just the next chapter in this ongoing process of galactic evolution. The story of Andromeda's formation and evolution is inextricably linked to the process of star formation that continues within its spiral arms today. These stellar nurseries represent the most active and dynamic regions of the galaxy. where new stars are constantly being born from the same interstellar material that has been recycled through generations of stars since the galaxy's formation. The most prominent star-forming regions in Andromeda are concentrated in a series of rings and spiral arms, visible as bright blue patches when the galaxy is observed in ultraviolet light. These blue colours come from massive, short-lived stars that burn hot and bright before exploding as supernovae after just a few million years, mere moments in astronomical timescales. Their presence indicates very recent star formation, as they don't live long enough to move far from their birthplaces. When observed in visible light with a moderate telescope, these star-forming regions appear as reddish patches along Andromeda's spiral arms. This red colour comes not from the stars themselves, but from glowing clouds of hydrogen gas that surround them. Young, massive stars emit large amounts of ultraviolet radiation that energizes nearby hydrogen atoms, causing them to glow with a characteristic red light astronomers call H-alpha emission. These glowing regions, technically known as HYI regions, where H is hydrogen and II indicates it's ionized, serve as beacons that pinpoint where star formation is actively occurring. One of the largest of these star-forming complexes in Andromeda is NGC 206, a massive cloud of gas and newly formed stars spanning more than 4,000 light-years. Within this single region, thousands of new stars have formed over the past few million years. If placed at the same distance as the famous Orion Nebula in our own galaxy, NGC 206 would cover a significant portion of our night sky. Star formation in these regions follows a relatively consistent process that astronomers have pieced together through observations of Andromeda and other galaxies. The process begins with giant molecular clouds, enormous concentrations of cold hydrogen gas and dust that can span hundreds of light years. These clouds are initially supported against gravitational collapse by their internal motion and magnetic fields, but various triggers can overcome these supporting forces. These triggers might include the shock wave from a nearby supernova explosion, collision with another gas cloud, or compression as the cloud passes through one of Andromeda's spiral density waves. Once a portion of the cloud begins to collapse, it fragments into smaller clumps, each of which may form a cluster of stars. The densest parts of these clumps become progressively hotter and more compressed until nuclear fusion ignites at their centres, giving birth to new stars. The most massive of these newborn stars quickly begin to affect their surroundings. Their intense ultraviolet radiation ionizes the surrounding gas, creating the glowing HII regions mentioned earlier. Their powerful stellar winds, streams of charged particles flowing outward from the stars, carve cavities in the remaining cloud, potentially triggering further star formation as they compress adjacent regions of gas. This process creates a complex feedback loop where star formation in one area can both inhibit and enhance star formation in neighbouring regions. Astronomers have identified thousands of these star-forming regions throughout Andromeda, with particular concentrations in a ring structure about 32,000 light-years from the galactic centre. This prominent ring of star formation, visible in multiple wavelengths from infrared to ultraviolet, appears to have been triggered by a density wave propagating through the galaxy's disk. Some theories suggest this wave may have originated from a past interaction with one of Andromeda's satellite galaxies, sending ripples through the galactic disk like a stone dropped in a pond. Studying star formation in Andromeda offers distinct advantages over studying similar processes in our own galaxy, within the Milky Way. Our view of many star-forming regions is obscured by the intervening dust in the galactic disk. Additionally, determining precise distances to objects within our own galaxy can be challenging. With Andromeda, astronomers can observe the entire galaxy from an outside perspective, making it easier to understand the global patterns of star formation and how they relate to the galaxy's larger structure. Observations across the electromagnetic spectrum reveal different aspects of Andromeda's star-forming regions. Radio telescopes detect the cold molecular gas that serves as the raw material for star formation. Infrared telescopes reveal warm dust heated by young stars, often identifying star-forming regions that are still hidden from optical view by thick clouds of dust. Ultraviolet and X-ray observations highlight the most energetic processes associated with the hottest, most massive stars and their violent deaths as supernovae. By combining these multi-wavelength observations, astronomers can construct a complete picture of the star formation cycle in Andromeda. They can identify regions in different stages of the process, from dense, cold clouds that have not yet begun forming stars, to active regions filled with young stellar objects still gathering mass from their surroundings, to mature clusters where stellar winds and supernova explosions have cleared away most of the remaining gas and dust. The rate of star formation in different regions of Andromeda provides important clues about the galaxy's current evolutionary state. While the galaxy as a whole forms approximately one solar mass worth of new stars each year, this activity is not uniformly distributed. The most active regions are found in the previously mentioned ring structure and along segments of the spiral arms, while the inner and outer portions of the disk show significantly less star formation. This pattern suggests that Andromeda may have already converted much of its available gas into stars in its central regions, while the ring represents a wave of star formation that has moved outward through the disk over time. The relatively low overall star formation rate compared to the galaxy's total mass indicates that Andromeda has passed its peak star-forming phase and is gradually transitioning toward a more quiescent state. The newly formed stars in these regions will ultimately determine Andromeda's future appearance and properties. The most massive will live brief, brilliant lives before exploding as supernovae, enriching the surrounding medium with heavy elements and potentially triggering the next generation of star formation. The longer-lived, lower-mass stars will continue to orbit within the galaxy for billions of years, gradually changing their properties as they age and evolve. Through detailed study of these star-forming regions, astronomers gain insight not just into Andromeda's current state, but into the fundamental processes that drive galaxy evolution throughout the universe. Each new generation of stars modifies the galaxy's composition, energy balance, and structure, continuing the long evolutionary journey that began with Andromeda's formation billions of years ago and will continue long into the future, even as it begins its momentous merger with our own Milky Way. The star-forming regions we observe in Andromeda today don't just produce stars, they create entire planetary systems. While we can directly observe the bright, massive stars that form in these stellar nurseries, they likely represent just the most visible component of a much richer cosmic ecology that includes countless planets orbiting stars throughout the galaxy. Although we cannot yet directly observe planets in Andromeda, what we've learned about exoplanets in our own galaxy allows astronomers to make educated estimates about the potential habitability of worlds in our neighbouring galaxy. With approximately 1 trillion stars, Andromeda likely hosts an extraordinary number of planets. Based on exoplanet studies from NASA's Kepler mission and other surveys, astronomers estimate that, on average, each star hosts at least one planet. More conservative estimates suggest Andromeda might contain about 100 billion planets, while higher estimates place the number closer to 2 trillion. Even at the lower end, the sheer number of potential worlds is staggering. Among this vast planetary population, how many might be habitable by life as we understand it? The concept of habitability typically centers on planets that can maintain liquid water on their surfaces, not so hot that water boils away, nor so cold that it remains permanently frozen. This Goldilocks zone, or habitable zone, depends primarily on a planet's distance from its star and the star's intrinsic brightness. Extrapolating from Kepler mission data, astronomers estimate that roughly 1 in 5 Sun-like stars hosts an Earth-sized planet in its habitable zone. If this ratio holds true throughout Andromeda, the galaxy could contain billions or even tens of billions of potentially habitable worlds. Even if we restrict our definition to planets very similar to Earth, rocky worlds with moderate temperatures, substantial atmospheres, and stable orbits, Andromeda would still likely host millions of such planets. The diversity of potential planetary environments in Andromeda would be enormous. The galaxy contains stars of all types, from tiny red dwarfs less than a tenth the mass of our Sun to massive blue giants dozens of times larger. Each type of star creates a different environment for its planets. Planets orbiting red dwarf stars, the most common stellar type, would need to orbit very closely to receive adequate warmth, potentially becoming tidally locked with one side permanently facing their star. Planets around massive, short-lived stars might experience intense radiation and relatively brief periods of stability before their stars explode as supernovae. The location within Andromeda would also significantly impact planetary habitability. In the galaxy's densely packed central bulge, stars are separated by much smaller distances than in our solar neighbourhood. A potentially habitable world there might experience night skies blazing with thousands of stars as bright as our full moon. The intense stellar density could also lead to more frequent close encounters with passing stars, potentially disrupting planetary orbits. Conversely, in Andromeda's outer regions, stars are more widely separated, and the galactic environment is generally quieter. However, these regions typically contain fewer heavy elements needed to build rocky planets like Earth. Planets in these outer reaches might be predominantly gas giants or ice worlds, with fewer rocky planets suitable for life as we know it. The spiral arms, where most star formation occurs, present yet another environment. Newly formed planetary systems in these regions would experience more supernovae, stellar radiation, and dynamic change than planets in quieter parts of the galaxy. This could either disrupt early life through sterilizing radiation or potentially accelerate evolution through increased mutation rates. Beyond location, the age of stars in different regions would create an additional dimension of diversity. Andromeda contains stars formed throughout its roughly 10 billion year history. The oldest stars, nearly as ancient as the universe itself, could host planetary systems where life has had almost 10 billion years to evolve, more than twice the time life has existed on Earth. If technological civilizations emerged on any of these ancient worlds, they could be billions of years more advanced than humanity. Younger star systems, particularly those in active star-forming regions, might host planets still in the early stages of evolution, perhaps similar to Earth billions of years ago when simple life was just beginning to emerge. The full range of evolutionary stages could be represented across Andromeda's vast collection of planetary systems. Unfortunately, directly detecting planets in Andromeda remains far beyond our current technological capabilities. Even in our own Milky Way, most exoplanets are detected indirectly through minute changes in their host star's light or motion. At Andromeda's distance of 2.5 million light-years, such subtle signals are completely undetectable with current instruments. We can only infer Andromeda's planetary population through statistical extrapolation based on what we've observed closer to home. This limitation means that any discussion of habitable worlds in Andromeda necessarily involves substantial speculation. However, based on our growing understanding of planetary formation and the apparent universality of physical laws, there's good reason to believe that planets, including potentially habitable ones, are abundant throughout Andromeda. If life has indeed emerged on some of these worlds, its nature would depend on countless variables unique to each planet's environment. Some might host nothing more complex than microbial mats, similar to Earth for most of its history. Others could potentially support complex multicellular organisms adapted to their particular planetary conditions. A few might even be home to intelligent species with their own civilizations, technologies, and understanding of the universe, perhaps including knowledge of our Milky Way as their neighbouring galaxy. Given the vast timescales involved, it's also possible that intelligent life in Andromeda has already risen, flourished, and disappeared many times over. Any technological civilizations that emerged on planets around the earliest stars could have existed for billions of years before Earth even formed. Whether such civilizations might survive for geological timescales or relatively briefly is one of the great unknowns in our understanding of cosmic evolution. As our ability to detect biosignatures, chemical indicators of life, in planetary atmospheres improves, we might someday be able to search for signs of life in nearby galaxies, though Andromeda's great distance will make it a particularly challenging target. For now, the question of habitable worlds and potential life in Andromeda remains in the realm of informed speculation, a tantalizing possibility supported by statistics but beyond our current ability to confirm. While we can only speculate about potential life in Andromeda, the galaxy's influence on human culture is well documented and spans thousands of years. Throughout history, this distant spiral has captured human imagination, appearing in our myths, art, science, and popular culture, a celestial presence that continues to evolve in significance as our understanding of the cosmos advances. Andromeda's cultural story begins with its visible presence in the night sky. As the most distant object visible to the naked human eye, it has been observed by countless generations across different civilizations. To early observers without telescopes, it appeared as a faint, fuzzy patch in the constellation that bears the same name, Andromeda, named after a princess in Greek mythology. The constellation's mythological origins trace back to the story of Princess Andromeda, daughter of King Cepheus and Queen Cassiopeia in ancient Greek legends. According to the myth, Cassiopeia boasted that her daughter was more beautiful than the Nereids, sea nymphs who were daughters of Poseidon. As punishment for this hubris, Poseidon sent a sea monster to ravage the kingdom. To appease the gods, Andromeda was chained to a rock as a sacrifice to the monster, but was rescued by the hero Perseus. This dramatic narrative was commemorated in the night sky through a group of constellations: Perseus, Andromeda, Cassiopeia, Cepheus, and Cetus, the sea monster. While the ancient Greeks recognized the constellation, they didn't necessarily identify the galaxy itself as a distinct cosmic object. The first recorded observation of the galaxy as a specific celestial feature comes from the Persian astronomer Abd al-Rahman al-Sufi, who described it in 964 CE as a little cloud in his Book of Fixed Stars. This early documentation demonstrates how the galaxy had drawn scientific attention even a millennium ago. In Western culture, Andromeda gained new significance following the realization in the early 20th century that it was a separate galaxy far beyond our Milky Way. This discovery fundamentally transformed humanity's conception of the universe and our place within it. The revelation that Andromeda was not just a nebula within our galaxy, but an entire island universe of stars dramatically expanded the scale of the cosmos in human understanding. This expansion of cosmic perspective has made Andromeda a powerful cultural symbol of the vastness of space. As the most distant object that can be seen without technological assistance, it represents a kind of natural boundary of human perception, the furthest we can see with our unaided eyes. This has given Andromeda a special significance as a tangible connection to the immensity of the universe. In visual arts, Andromeda has been a subject of fascination for centuries. Early astronomical illustrations often depicted the Andromeda Nebula as a swirling cloud, reflecting the limited understanding of its true nature. After its identification as a separate galaxy, it began appearing in more scientifically accurate representations. Modern astrophotography has captured increasingly detailed and stunning images of Andromeda, making it one of the most photographed and visually recognized galaxies. These images have transcended pure scientific documentation to become cultural artifacts in their own right. Photographs of Andromeda appear not just in astronomy textbooks, but on posters, clothing, jewelry, and as decorative elements in homes and public spaces. The galaxy's spiral structure, with its bright core and sweeping arms, has become an iconic representation of cosmic beauty and order. In literature and popular culture, Andromeda features prominently in science fiction as both setting and symbol. The Andromeda strain by Michael Crichton borrowed the galaxy's name for its extraterrestrial pathogen, while the television series Andromeda used the galaxy as the setting for its space opera narrative. In Isaac Asimov's Foundation series, Andromeda represents the frontier of potential human expansion beyond the Milky Way, a distant goal for a civilization spanning millions of worlds. The discovery that Andromeda is on a collision course with our Milky Way has added another layer to its cultural significance. This future cosmic event, though scheduled for billions of years from now, has captured public imagination as both an existential scenario and a reminder of the dynamic, ever-changing nature of the universe. Popular science articles, documentaries, and digital simulations of this future collision have made it one of the most widely known astronomical predictions. For amateur astronomers, Andromeda holds special significance as a favourite observational target, often one of the first galaxies that beginning stargazers seek out. Locating Andromeda through binoculars or a small telescope has become a rite of passage in amateur astronomy. The experience of personally observing this distant galaxy creates a powerful connection to the cosmos that many find profoundly moving, a direct visual link to something millions of light years away. Andromeda has also taken on educational significance as a teaching tool. Its status as our largest galactic neighbour makes it an ideal example for explaining concepts like galactic structure, stellar evolution, and cosmic distances. In classrooms around the world, Andromeda serves as a concrete example that helps students grasp abstract astronomical concepts. The galaxy's role in human culture continues to evolve with advances in our understanding. Each new discovery about Andromeda, from the properties of its supermassive black hole to the details of its satellite galaxy system, finds its way into public consciousness through news reports, documentaries, and social media. This ongoing scientific narrative keeps Andromeda present in contemporary culture in ways that blend scientific fact with wonder. Even the light travel time from Andromeda has entered popular understanding as a way of conceptualizing deep time. The knowledge that we see Andromeda as it was 2.5 million years ago, when our early human ancestors were just beginning to use stone tools, provides a visceral connection between cosmic and human timescales. This perspective makes Andromeda not just a distant astronomical object, but a kind of time capsule visible in our night sky. As humanity's understanding of the universe continues to grow, Andromeda's cultural significance will likely continue to evolve. Its status as our galactic neighbour, its visibility to the naked eye, its approaching collision with our galaxy, and its sheer beauty ensure that it will remain a significant celestial landmark in human culture, a distant spiral that connects us to the larger cosmic environment we inhabit. Andromeda's cultural significance extends beyond our artistic and literary representations, intersecting with cutting-edge science through one of the most profound mysteries in modern physics, dark matter. This invisible substance appears to make up the majority of Andromeda's mass and plays a crucial role in shaping its structure and evolution. Despite never having been directly detected, dark matter's presence in Andromeda provides some of the most compelling evidence for its existence throughout the universe. Astronomers estimate that approximately 90% of Andromeda's total mass consists of dark matter, creating an enormous halo that extends far beyond the visible boundaries of the galaxy. This invisible component dwarfs the combined mass of all the galaxy's stars, gas, dust, and even its central supermassive black hole. Yet despite its overwhelming contribution to the galaxy's mass, dark matter neither emits nor absorbs light at any wavelength, making it impossible to observe directly with conventional telescopes. So how do scientists know it's there? The primary evidence comes from studying the motion of stars and gas within Andromeda. According to the laws of physics established by Newton and Einstein, the speed at which objects orbit a central mass depends on the amount of matter inside their orbit. More mass leads to faster orbital velocities at a given distance. When astronomers measured the rotation speeds of stars and gas clouds at different distances from Andromeda's centre, they found something surprising. Instead of decreasing at greater distances, as would be expected based on the visible matter alone, the rotation speeds remained relatively constant far into the outer regions of the galaxy. This flat rotation curve, DOT, as astronomers call it, presents a fundamental problem. If the only matter in Andromeda were the stars, gas, and dust we can see, the gravitational force would be insufficient to maintain the observed orbital speeds. Stars in the outer regions would be moving too fast to remain bound to the galaxy and would fly off into intergalactic space. The fact that Andromeda maintains its structure indicates there must be substantially more mass present than what we can see. This invisible component is what we call dark matter. The dark matter halo surrounding Andromeda isn't a uniform sphere, but has a complex structure that astronomers are still working to map in detail. Computer models suggest the halo is somewhat flattened rather than perfectly spherical, and its density decreases with distance from the galactic center according to specific mathematical patterns. The exact shape and density profile of this halo provide important clues about the nature of dark matter itself. Within the scientific community, there are several leading theories about what dark matter actually is. The most widely accepted idea suggests it consists of a new type of subatomic particle that interacts with normal matter almost exclusively through gravity. These hypothetical particles, with names like WIMPs, weakly interacting massive particles, or axions, would have been created in abundance during the Big Bang and would have gradually clumped together under their mutual gravitational attraction. These dark matter clumps would have formed the initial gravitational scaffolding upon which Andromeda and all other galaxies eventually formed. Ordinary matter, the hydrogen and helium gas from the early universe, would have fallen into these dark matter concentrations, becoming dense enough to form stars and, eventually, the spiral structure we see today. In this way, dark matter didn't just contribute to Andromeda's mass, but played a fundamental role in its very formation. The influence of dark matter extends beyond Andromeda's internal structure to its interactions with satellite galaxies. The movements of these smaller galaxies around Andromeda are determined largely by the gravitational pull of the dark matter halo. By carefully tracking the velocities of these satellites, astronomers can probe the extent and distribution of dark matter at distances far beyond the visible edge of the galaxy. Particularly intriguing is the apparent arrangement of many satellite galaxies in a thin plane around Andromeda, similar to the arrangement observed around our Milky Way. This organized structure doesn't match predictions from simple dark matter models, which suggest satellites should be distributed more randomly. This discrepancy might indicate something important about the properties of dark matter or the history of how these satellite systems formed. When Andromeda and the Milky Way eventually begin their collision process, the interaction will actually be dominated initially by their dark matter halos. These extended structures will begin to interact long before the visible portions of the galaxies make contact. The gravitational effects of these overlapping halos will influence the paths of stars in both galaxies, beginning the process of disruption that will eventually lead to their complete merger. Understanding dark matter in Andromeda has implications far beyond this single galaxy. As our closest large galactic neighbour, Andromeda provides a unique laboratory for testing theories of dark matter that can then be applied throughout the universe. If scientists could definitively determine the nature and properties of dark matter by studying Andromeda, it would resolve one of the most significant outstanding questions in physics and cosmology, despite decades of research and increasingly sophisticated observations. Dark matter remains one of the great unsolved mysteries in science. Particle physics experiments on Earth have yet to definitively detect dark matter particles, though numerous projects worldwide continue the search. For now, the evidence from Andromeda and other galaxies provides our most compelling indication that this invisible substance is real and plays a crucial role in shaping the cosmos. As we continue to study Andromeda's dark matter halo and compare it to our own galaxy's dark matter distribution, Patterns emerge that help us understand not just these specific galaxies, but the fundamental physics that governs galactic formation and evolution throughout the universe. The mystery of dark matter reminds us that despite all our technological advances, there remain fundamental aspects of even our closest galactic neighbour that we have yet to fully understand. While dark matter represents a profound similarity between Andromeda and our Milky Way, both are dominated by this invisible substance, there are many important differences between these two spiral galaxies. Comparing Andromeda with our home galaxy provides valuable insights into galactic evolution and helps us better understand our own cosmic neighbourhood. The most obvious difference between the two galaxies is their size. Andromeda is substantially larger than the Milky Way, with a diameter of approximately 220,000 light-years compared to the Milky Way's 100,000 light-years. This greater expanse contains significantly more stars. Andromeda hosts approximately 1 trillion stars, while estimates for the Milky Way range from 200 billion to 400 billion. This size difference means that in the eventual merger, Andromeda will be the dominant partner, contributing more mass to the final combined galaxy. The stellar mass isn't the only area where Andromeda outweighs our galaxy. Its central supermassive black hole, as mentioned earlier, is much more massive than our own Sagittarius A star. While the Milky Way's central black hole contains approximately 4 million solar masses, Andromeda's behemoth weighs in at 100 million to 240 million solar masses, roughly 50 times larger. This significant difference suggests the two galaxies may have experienced different histories of mergers and accretion events that built up their central black holes. Structurally, both galaxies are classified as spiral galaxies with bars, central elongated structures of stars that cross through their cores. However, their spiral arm patterns differ notably. The Milky Way appears to have 4 major spiral arms, though there's ongoing debate among astronomers about the exact number and arrangement, while Andromeda's spiral structure is more complex, with multiple arms that sometimes appear fragmented or ring-like rather than forming continuous spirals. One of Andromeda's most distinctive features is its series of concentric rings where star formation is concentrated, particularly a prominent ring about 32,000 light-years from the centre. The Milky Way doesn't show such well-defined ring structures, instead having its star formation more evenly distributed along its spiral arms. These different patterns of star formation suggest the galaxies have experienced different histories of disturbances or internal evolutionary processes. The current rate of star formation also differs between the two galaxies. The Milky Way forms new stars at a rate of about 1 to 3 solar masses per year, while Andromeda's star formation has slowed to about 1 solar mass annually despite having more raw material available. This lower efficiency at converting gas into new stars indicates Andromeda may be at a more advanced stage in its evolutionary cycle. This difference in star formation efficiency connects to another contrast: the overall colour of the two galaxies. Andromeda appears slightly redder when viewed as a whole, reflecting its larger population of older, redder stars and somewhat reduced rate of forming new, blue stars. The Milky Way, while still dominated by older stars in its total stellar mass, has proportionally more active star formation producing young, blue stars that contribute to a slightly bluer overall appearance. The two galaxies also differ in their globular cluster populations. These ancient balls of stars orbit in the halos of both galaxies, but Andromeda possesses approximately 450 globular clusters compared to the Milky Way's estimated 150. This larger population might reflect Andromeda's greater mass, or it might indicate different histories of acquiring these clusters through past galactic mergers. Examining the chemical composition of the two galaxies reveals additional differences. Astronomers use the term metallicity to describe the proportion of elements heavier than hydrogen and helium in a star or gas cloud. Both galaxies show a gradient in metallicity, with higher concentrations of heavy elements toward their centres. However, studies suggest Andromeda has a somewhat higher overall metallicity than the Milky Way, particularly in its outer regions. This higher concentration of heavy elements indicates Andromeda may have experienced more generations of star formation and supernova enrichment throughout its history. The satellite galaxy systems surrounding each galaxy also show interesting contrasts. Both are accompanied by dozens of smaller galaxies. But Andromeda's satellites include more relatively massive companions. The Triangulum galaxy, M33, which may be a satellite of Andromeda, is substantially larger than any of the Milky Way's satellite galaxies. The Large Magellanic Cloud, our largest satellite, contains only about 1/10 the mass of Triangulum. This difference in satellite populations might reflect the different environments in which the two galaxies formed or different histories of interactions with neighbouring galaxies. The dark matter halos surrounding both galaxies, while similar in their overall dominance of the total mass, appear to have different shapes and density profiles. Observations suggest Andromeda's dark matter might be more concentrated toward its centre than the Milky Way's, though measuring dark matter distributions remains challenging and these conclusions are still somewhat tentative. There are also differences in the gas content and distribution between the two galaxies. While both contain extensive reservoirs of hydrogen gas, the fuel for future star formation, the Milky Way appears to have a higher ratio of gas to stars. Andromeda has apparently converted a greater percentage of its original gas supply into stars, consistent with the idea that it's in a more advanced evolutionary state than our galaxy. When observed in X-ray wavelengths, Andromeda shows a more prominent hot gas halo than the Milky Way. This extremely hot, tenuous gas extends far beyond the visible boundaries of both galaxies, but appears more extensive around Andromeda. This difference might relate to Andromeda's greater mass and its history of interactions with satellite galaxies. Perhaps the most significant similarity between the two galaxies is their shared future, despite their differences. Andromeda and the Milky Way are gravitationally bound to each other and destined to merge into a single elliptical galaxy. During this process, many of their current distinctions will be erased as their stars, gas, and dark matter combine into a new structure unlike either of the original spiral galaxies. Studying the similarities and differences between these two giant spiral galaxies provides astronomers with a unique opportunity to understand galactic evolution. By comparing two similar but distinct systems at approximately the same cosmic epoch, researchers can identify which features are universal to spiral galaxies of their size and which might result from their unique formation histories or environmental influences. As our closest large galactic neighbour, Andromeda serves as a crucial reference point for understanding our own Milky Way and, by extension, spiral galaxies throughout the universe. Beyond the visible differences between Andromeda and our Milky Way lies another important but often overlooked feature that shapes both galaxies, their magnetic fields. While invisible to the human eye, these vast cosmic force fields play crucial roles in galactic evolution, affecting everything from star formation to the movement of charged particles throughout the galaxy. Andromeda's magnetic field, like that of all spiral galaxies, represents one of its most extensive but least understood components. Magnetic fields in galaxies like Andromeda are incredibly weak compared to those we encounter in everyday life, typically just a few microgauss in strength, which is about 100,000 times weaker than Earth's magnetic field. Despite this relative weakness, these fields extend throughout the entire galaxy, influencing processes across hundreds of thousands of light years. The sheer scale of these fields makes them significant forces in galactic evolution. Astronomers detect Andromeda's magnetic field primarily through radio observations. When electrons move through a magnetic field, they emit radiation called synchrotron emission, which is particularly strong at radio wavelengths. By mapping this emission, researchers can trace the structure and strength of the magnetic field throughout the galaxy. Additional information comes from measuring the polarization of light passing through magnetized regions, as magnetic fields cause light waves to rotate slightly in a process called Faraday rotation. These observations reveal that Andromeda's magnetic field follows a pattern broadly similar to other spiral galaxies. The field tends to align with the spiral arms, creating orderly structures that trace the galaxy's overall spiral pattern. This alignment isn't coincidental, it results from the same processes that generate the spiral arms themselves. As the galaxy rotates, both the matter forming the spiral arms and the magnetic field lines become stretched and aligned along the arms. Near the centre of Andromeda, the magnetic field becomes stronger and more turbulent, likely influenced by the concentrated mass of stars and the supermassive black hole's activity. In the outer regions, the field becomes weaker but more ordered, often showing elegant spiral patterns that extend beyond the visible boundaries of the galaxy. The origin of Andromeda's magnetic field, like those of other galaxies, remains somewhat mysterious. Astronomers believe these large-scale fields evolved through a process called the galactic dynamo effect. This process begins with a weak primordial magnetic field, perhaps created in the early universe or during the galaxy's initial formation. As Andromeda rotates, the combination of rotational motion and turbulence in its gas gradually amplifies and organizes this initial field. Over billions of years, this dynamo action has strengthened the field to its current state. One of the most significant roles of Andromeda's magnetic field is its influence on star formation. When interstellar gas clouds collapse to form new stars, magnetic fields can either hinder or help the process. By providing pressure support against gravity, magnetic fields can temporarily slow a cloud's collapse, potentially regulating the rate of star formation. However, magnetic fields also help remove angular momentum from rotating clouds, which can actually facilitate collapse under the right conditions. The exact balance of these opposing effects depends on the specific conditions in different regions of Andromeda. Observations of star-forming regions in Andromeda show that magnetic fields are often compressed and strengthened in these areas. The increased density of both gas and magnetic field lines creates complex interactions that can trigger or suppress the birth of new stars. In some cases, the magnetic field lines channel gas flow along specific paths, creating filamentary structures that eventually fragment into multiple stars. Beyond star formation, magnetic fields play crucial roles in many other aspects of Andromeda's physics. They help confine cosmic rays, high-energy charged particles that would otherwise escape into intergalactic space. By trapping these particles, magnetic fields contribute to the pressure balance within the galaxy and influence the temperature and ionization state of the interstellar medium. Magnetic fields also affect the flow of gas throughout Andromeda. Charged particles in ionized gas tend to follow magnetic field lines, creating preferred directions for gas flow. This directional influence can help channel gas inward towards star-forming regions or outward in galactic winds. During more energetic events like supernova explosions, magnetic fields help shape the expanding shock waves and can be compressed and amplified in the process. Looking toward the future collision between Andromeda and our Milky Way, magnetic fields will play an interesting role in the merger process. When the galaxies begin to interact, their magnetic fields will also come into contact, potentially reconnecting and releasing energy in complex ways. Computer simulations suggest that the merger will temporarily strengthen and disorder both galaxies' magnetic fields before they eventually settle into a new configuration in the merged galaxy. This magnetic disturbance could influence star formation rates during the collision by altering how gas clouds compress and collapse. Recent observations have revealed additional complexity in Andromeda's magnetic field. Rather than being a simple spiral pattern, the field contains numerous substructures, reversals, and loops that reflect the galaxy's dynamic nature. Some of these features may be related to past interactions with satellite galaxies or localized events like star formation bursts or supernova explosions. Particularly interesting are the vertical components of Andromeda's magnetic field, portions that extend above and below the galactic disk. These vertical fields may help drive galactic fountains, processes where hot gas rises from the disk, cools, and then falls back. This circulation helps distribute newly formed heavy elements throughout the galaxy and plays a role in regulating ongoing star formation. Andromeda's magnetic field also interacts with its surrounding environment. The boundary where the galaxy's field meets the intergalactic medium creates a magnetopause similar in concept, though vastly different in scale, to the one where Earth's magnetic field meets the solar wind. This boundary helps shield the galaxy from some external particles while also controlling how material enters and leaves the galactic system. Understanding Andromeda's magnetic field helps astronomers piece together a more complete picture of how spiral galaxies function as integrated systems. The field represents one of several forms of energy, alongside gravity, thermal energy, and turbulence, that work together to determine the galaxy's overall structure and evolution. The balance between these forces helps explain everything from the galaxy's rotation curve to its star formation history. As technological capabilities advance, future radio telescopes will provide increasingly detailed maps of Andromeda's magnetic field, revealing its structure with unprecedented clarity. These improved observations will help refine our understanding of how magnetic fields shape galactic evolution, not just in Andromeda, but throughout the universe. While Andromeda's magnetic field subtly shapes the galaxy over millions and billions of years, supernovae represent the most energetic and rapidly transformative events in any galaxy's life cycle. These stellar explosions, occurring regularly throughout Andromeda, inject enormous amounts of energy into the surrounding environment while seeding the galaxy with heavy elements necessary for planet formation and potential life. By studying supernovae in Andromeda, astronomers gain valuable insights into these cosmic explosions that would be impossible to obtain from supernovae in our own galaxy. Andromeda experiences approximately one supernova explosion every 30 to 50 years on average, a rate roughly comparable to our Milky Way. Given that light takes 2.5 million years to reach us from Andromeda, we're essentially watching these explosions with a substantial time delay. The supernovae we detect today actually exploded during Earth's Pleistocene epoch, when early human ancestors were just beginning to use stone tools. Astronomers classify supernovae into several types based on their light curves, how their brightness changes over time, and spectral features, the specific wavelengths of light they emit. The two broadest categories are Type 1a and Type 1I. Type Ia supernovae occur in binary star systems when a white dwarf, the dense remnant of a sun-like star, accumulates material from a companion star until it reaches a critical mass and explodes. Type 2 supernovae represent the deaths of massive stars that have exhausted their nuclear fuel and collapse under their own gravity. Both types of supernovae occur regularly in Andromeda, and each provides different information about the galaxy. Type Ia supernovae are particularly valuable as standard candles for measuring cosmic distances because they all reach approximately the same peak brightness. Early measurements of Type Ia supernovae in Andromeda helped astronomers establish its distance with unprecedented accuracy, confirming it as a separate galaxy far beyond our own. Type 2 supernovae, meanwhile, tell us about the population of massive stars in Andromeda. Since these stars live only a few million years before exploding, their supernovae trace regions of recent star formation. The distribution of Type 2 supernovae in Andromeda confirms that most massive star formation occurs in the galaxy's spiral arms and ring structures, particularly in the prominent star-forming ring about 32,000 light-years from the centre. When a star explodes as a supernova in Andromeda, it briefly outshines millions of ordinary stars for a period of several weeks. A single supernova can emit as much energy as the entire galaxy, despite Andromeda's great distance. These explosions can be detected with moderate-sized telescopes from Earth. In fact, amateur astronomers regularly participate in supernova searches, scanning images of Andromeda for new points of light that weren't present in previous observations. The most recent naked-eye visible supernova in Andromeda occurred in 1985, designated SN 1985F. It reached a maximum brightness visible with binoculars from dark sky locations on Earth. Professional and amateur astronomers around the world followed its evolution over several months as it brightened and then gradually faded from view. After the initial brilliance of a supernova fades, the explosion leaves behind an expanding shell of gas and debris called a supernova remnant. These remnants persist for tens of thousands of years, gradually dispersing their energy and material into the surrounding interstellar medium. Andromeda contains hundreds of these supernova remnants in various stages of evolution, each marking the site of a stellar explosion from the recent to distant past. Supernova remnants in Andromeda are most easily detected in X-ray and radio wavelengths. B. In X-rays, the extremely hot gas in young remnants shines brightly, while radio observations detect synchrotron radiation produced as electrons spiral through magnetic fields in the remnant. By studying remnants of different ages, astronomers can track how supernova energy dissipates over time and how remnants interact with their surroundings. These remnants play several crucial roles in Andromeda's ecology. First, they inject enormous amounts of energy into the interstellar medium, heating gas and generating turbulence that can either trigger or prevent further star formation depending on local conditions. This energy input helps maintain the delicate balance between gravitational collapse and various forms of pressure support that regulate star formation throughout the galaxy. Second, supernovae are the primary source of elements heavier than iron in Andromeda and all galaxies. Elements like gold, silver, lead, dot, and uranium can only be created during the extreme conditions of supernova explosions, when these explosions scatter their newly forged elements into space. They enrich the interstellar medium from which future generations of stars and planets will form. Without this enrichment process, repeated over billions of years, rocky planets like Earth could never have formed. The rate and distribution of supernovae in Andromeda tell us about the galaxy's star formation history. Regions with more supernova remnants generally experienced more active star formation in the recent cosmic past. By mapping these remnants, astronomers can reconstruct patterns of star formation across Andromeda over the last few million years. This distribution shows that while star formation occurs throughout much of the galaxy's disk, it's particularly concentrated in the spiral arms and ring structures. Supernova remnants also provide natural laboratories for studying extreme physics. The shock waves from these explosions can accelerate particles to nearly the speed of light, creating cosmic rays that fill the galaxy. By studying how supernova remnants evolve in Andromeda, astronomers gain insights into the origin of cosmic rays and other high-energy phenomena without the complications of studying them within our own galaxy, where our position inside the disk limits our perspective. Perhaps most interestingly, supernovae in Andromeda give us a preview of events that also occur in our own galaxy, but are often hidden from our view by interstellar dust. When a supernova explodes in the Milky Way, it's often obscured from Earth-based observers by the thick lanes of dust in our galactic disk. Andromeda, however, offers a clearer external perspective. By studying the full population of supernovae and their remnants in Andromeda, astronomers gain a more complete picture of these cosmic explosions than we could obtain from our inside view of the Milky Way. Each supernova in Andromeda represents both an ending and a beginning, the death of a star and the birth of new possibilities as its elements disperse to potentially form new stars, planets, and eventually, perhaps, life itself. This cosmic recycling process, repeated countless times throughout Andromeda's history, has gradually transformed the galaxy's composition from the simple hydrogen and helium of its birth to the complex mixture of elements present today. The supernovae that regularly erupt across Andromeda don't just create spectacular light shows and forge heavy elements, they play a crucial role in shaping the galaxy's interstellar medium. The vast collection of gas and dust that fills the space between stars, This complex mixture of material serves as both the remnant of past stellar generations and the raw material for future stars, creating a cosmic ecosystem that recycles matter throughout the galaxy's lifetime. The interstellar medium, ISM, in Andromeda consists primarily of hydrogen in various forms, from cold molecular clouds to hot ionized plasma. Approximately 90% of the atoms in this medium are hydrogen, with helium making up most of the remainder. However, the remaining tiny fraction of heavier elements, carbon, oxygen, silicon, iron, and others, plays a disproportionately important role in the medium's properties and in the galaxy's evolution. This gas isn't distributed uniformly throughout Andromeda, but instead forms a complex network of structures with enormous variations in density. The most tenuous regions contain just a few atoms per cubic meter, a vacuum more perfect than anything we can create on Earth. At the other extreme, dense molecular clouds can contain millions or billions of atoms per cubic meter, though this is still far less dense than the air we breathe. Among the most striking features visible in radio observations of Andromeda's interstellar medium is a series of ring-like structures of hydrogen gas. The most prominent is the same 32,000 light-year ring mentioned earlier in connection with star formation. This concentration of gas forms the primary reservoir for ongoing star formation in the galaxy. Other, less distinct rings at different distances from the centre suggest a complex history of disturbances, perhaps caused by density waves, interactions with satellite galaxies, or even past minor mergers that have shaped the distribution of gas. Interspersed throughout this gas is a fine distribution of tiny solid particles collectively known as cosmic dust. These dust grains, typically less than a micrometer in size, are composed primarily of carbon compounds and silicates, essentially tiny grains of soot and sand. Despite making up only about 1% of the interstellar medium's mass, dust has a profound effect on how we observe Andromeda and on the galaxy's internal processes. When viewed through optical telescopes, dust appears most prominently as dark lanes cutting across Andromeda's disk. These dust lanes, appearing as shadowy bands against the bright background of stars, trace the spiral structure of the galaxy and are particularly concentrated along the spiral arms. They're visible because dust absorbs and scatters visible light, blocking our view of stars behind them. This obscuring effect of dust creates a significant observational challenge. When astronomers look at Andromeda in visible light, the dust lanes hide many stars and regions of interest, particularly toward the far side of the galaxy. This is where observations at different wavelengths become crucial. Infrared light can penetrate dust much more effectively than visible light, revealing stars and structures that would otherwise remain hidden. Radio waves pass through dust almost unimpeded, allowing astronomers to map the distribution of gas throughout the entire galaxy. When observed in the far infrared portion of the spectrum by telescopes like the Herschel Space Observatory, Andromeda reveals a different face entirely. Instead of appearing dark, the dust glows brightly in infrared as it absorbs energy from nearby stars and re-radiates it at longer wavelengths. These infrared observations show that dust is concentrated in the same regions where cold gas is most abundant, primarily along the spiral arms and in the ring structures mentioned earlier. The interstellar medium in Andromeda doesn't simply sit static, it's constantly in motion, driven by energy inputs from various sources. Radiation from hot stars pushes on dust grains, stellar winds inject momentum, and supernova explosions create expanding bubbles that sweep up material as they grow. These processes create a turbulent, constantly changing environment where gas can be compressed in some regions while being dispersed in others. This dynamic nature of the interstellar medium plays a crucial role in regulating star formation throughout Andromeda. When gas clouds become sufficiently dense, they can collapse under their own gravity to form new stars. However, energy input from existing stars, particularly massive ones that emit intense radiation and eventually explode as supernovae, can disrupt nearby clouds. temporarily halting star formation in those regions. This creates a self-regulating cycle where star formation in one area can both trigger new star formation in adjacent regions through compression of gas, while simultaneously limiting it in others through dispersal of gas. The balance of these opposing effects helps explain why Andromeda forms stars at a relatively steady rate, rather than converting all its gas into stars at once or ceasing star formation entirely. The chemical composition of Andromeda's interstellar medium tells the story of the galaxy's evolutionary history. When Andromeda first formed billions of years ago, its gas consisted almost entirely of hydrogen and helium, the primary elements created in the Big Bang. Over time, successive generations of stars have fused these light elements into heavier ones and then returned them to the interstellar medium through stellar winds and supernova explosions. Modern observations show that the metallicity, the abundance of elements heavier than helium, varies significantly throughout Andromeda. The central regions contain the highest proportion of heavy elements, likely because star formation has proceeded through more generations there. The outer regions show lower metallicity, indicating fewer completed cycles of stellar birth and death. This gradient in chemical composition provides important clues about how the galaxy has evolved over cosmic time. Within the interstellar medium, complex chemistry occurs on the surfaces of dust grains, where atoms and simple molecules can stick, interact, dot, and form more complex compounds. Observations of Andromeda in specific wavelengths reveal the presence of various molecules, from simple ones like carbon monoxide, which astronomers use to trace the distribution of molecular hydrogen, to more complex organic compounds. This molecular component of the interstellar medium is particularly important for star formation, as it forms the densest clouds from which new stars are born. The dust component of Andromeda's interstellar medium also plays several crucial roles beyond simply absorbing light. Dust grains provide surfaces where hydrogen atoms can combine to form molecular hydrogen, the primary ingredient in star-forming clouds. They shield molecules from destructive ultraviolet radiation, allowing complex chemistry to proceed in protected environments. And when new stars and planetary systems form, the dust provides the solid materials needed to build rocky planets like Earth. When Andromeda and the Milky Way begin their collision process billions of years from now, their respective interstellar media will be among the first components to interact, unlike stars, which are unlikely to physically collide due to the vast spaces between them. Gas clouds from the two galaxies will directly impact one another, creating shock waves, compression, and dramatically enhanced star formation in the regions of overlap. This future collision will fundamentally transform both galaxies, eventually creating a single dot, massive elliptical galaxy that astronomers have informally named Milkomeda or Lactomeda. Unlike the spiral galaxies that will merge to create it, this final galaxy will have a three-dimensional ellipsoidal shape without the distinctive disk and spiral arm structures that characterize both Andromeda and the Milky Way today. The transformation will unfold over several billion years through a complex dance of gravity. The first close approach between the galaxies will occur in approximately 4.5 billion years, though the exact timing remains somewhat uncertain due to the difficulty of precisely measuring Andromeda's sideways motion relative to our galaxy. This initial encounter won't result in an immediate merger, but will dramatically disrupt both galaxies, distorting their spiral structures into long streamers and arcs of stars. After this first pass, the galaxies will move apart again before gravity pulls them back for additional encounters, each more disruptive than the last. Computer simulations suggest that a complete merger will take an additional 2 to 3 billion years after the initial approach, with the process finishing perhaps 7 billion years from now. During these repeated encounters, the interstellar gas in both galaxies will experience significant compression when the gas clouds collide. This compression will trigger an intense burst of star formation, what astronomers call a starburst, that may increase the star formation rate by a factor of 10 or more compared to current levels. This starburst will be particularly intense during the closest approaches of the two galaxies. This period of enhanced star formation will consume a significant portion of the gas reservoirs of both galaxies. The remaining gas will be heated by the energy released from the starburst and from the general gravitational disruption of the merger. Much of this heated gas will be ejected from the inner regions of the merging galaxies, forming an extended halo of hot gas around the remnant. The fate of the dust components of both galaxies will mirror that of the gas. Some dust will be incorporated into new stars formed during the starburst phase. Some will be heated and destroyed by the intense radiation from newly formed massive stars. The remainder will be redistributed throughout the merged galaxy, generally becoming more diffuse as the compact disks of the original spirals transform into the more extended distribution of an elliptical galaxy, while the gas and dust experience direct collisions. The stars themselves will primarily respond to the changing gravitational fields without physically colliding. The orderly rotational motion that characterizes both spiral galaxies today will be transformed into more random orbital patterns. Stars originally in the disks of either galaxy may end up on elongated orbits that take them far from the center of the merged galaxy, while others may settle into more circular orbits within the central regions. Perhaps the most dramatic single event in the entire merger process will be the coalescence of the supermassive black holes from the centers of both galaxies. Initially, these black holes, 4 million solar masses for the Milky Ways and 100 to 240 million solar masses for Andromedas, will orbit each other within the merging core of the combined galaxy. Over time, gravitational interactions with surrounding stars will cause their orbit to shrink until they get close enough for gravitational waves to carry away their remaining orbital energy, causing them to merge into a single, even more massive black hole. This black hole merger will release an enormous amount of energy in the form of gravitational waves, ripples in the fabric of spacetime itself. While these waves won't directly affect the visible structure of the galaxy, they represent one of the most energetic single events that will occur during the entire merger process. The final galaxy that emerges from this extended merger will look very different from either Andromeda or the Milky Way. Instead of a flattened disk with spiral arms, it will have a smooth, ellipsoidal shape with a bright central core that gradually fades into an extended halo. The distinctive dust lanes of the spiral galaxies will be gone, as will most of the cold gas that currently fuels star formation in both galaxies. This transformation from spirals to an elliptical galaxy reflects a common evolutionary pathway in the universe. Many of the elliptical galaxies we observe today are thought to have formed through similar merger processes between spiral galaxies. In this sense, the future Andromeda represents a normal stage in galaxy evolution rather than an unusual outcome. The stellar population of this final galaxy will also differ from its progenitors. After the starburst phase consumes much of the remaining gas, new star formation will largely cease. Over time, the bright blue stars created during the starburst will live out their short lives, leaving behind a population dominated by older, redder stars. This will give the merged galaxy the characteristic reddish color observed in elliptical galaxies today. Despite the dramatic nature of this transformation, it's worth noting that any planetary systems orbiting stars in either galaxy, including our own solar system, if it still exists, are unlikely to be directly affected by the merger process. The vast distances between stars mean that direct stellar collisions will be extremely rare, and most planetary systems will simply find themselves carried along on new trajectories through the merged galaxy. By the time this merger completes, the Sun will have long since exhausted its hydrogen fuel and evolved into a red giant, potentially engulfing the inner planets of our solar system. Whether Earth will survive this stellar evolution remains uncertain, but the merger itself poses no direct threat to our planet. The night sky would, however, change dramatically over time for any observers on Earth, with Andromeda growing to fill a large portion of the sky during close approaches and new, unfamiliar constellations forming as stars are redistributed throughout the merging galaxies. The Andromeda galaxy that eventually forms will be one of the dominant galaxies in our local cosmic neighbourhood, substantially larger than either of its progenitor galaxies. As an elliptical galaxy with little ongoing star formation, it will gradually continue to evolve, but much more slowly than either spiral galaxy does today. Over many more billions of years, its stars will age and die. Its distribution will become more uniform through continued gravitational interactions, and it will settle into the relatively quiescent existence typical of large elliptical galaxies throughout the universe. While the formation of Andromeda represents a cosmic event billions of years in our future, it's natural to wonder what life on Earth might experience during this galactic merger. Though the collision itself poses no direct threat to our planet, the time frame involved coincides with significant changes in our solar system that will fundamentally alter Earth's habitability long before the galaxies complete their dance. By the time Andromeda and the Milky Way begin their initial approach 4.5 billion years from now, conditions on Earth will have already changed dramatically due to our Sun's natural evolution. Stars like our Sun gradually increase in luminosity as they age, a consequence of their cores becoming more compact and hot as hydrogen is converted to helium through nuclear fusion. Astronomical models predict that the Sun will become approximately 40% more luminous than it is today by the time the galactic collision begins. This increased solar brightness will have profound implications for Earth's climate system, with significantly more solar energy reaching our planet. Surface temperatures will rise substantially. Earth's oceans will experience accelerated evaporation, increasing atmospheric water vapour, itself a potent greenhouse gas. This could potentially trigger a runaway greenhouse effect similar to what occurred on Venus billions of years ago, where water vapour in the upper atmosphere breaks down, hydrogen escapes to space, and the planet's water is permanently lost. Most climate models suggest that Earth's oceans will begin to boil away between 1 and 2 billion years from now, well before the galactic collision begins. By the time Andromeda makes its first close approach to our galaxy, Earth may have already transformed from the blue, water-rich world we know today into a hot, dry planet inhospitable to most forms of complex life that currently exist. During this same period, geological processes on Earth will continue. Plate tectonics, the movement of Earth's crustal plates, will rearrange continents into new configurations. Carbon dioxide levels may decrease as silicate weathering continues without the moderating feedback of plant life, potentially causing the planet to cool somewhat despite the brightening sun. However, these cooling effects would likely be insufficient to counteract the dramatic increase in solar luminosity. The changes become even more extreme approximately 1 billion years after the initial approach of Andromeda, or roughly 5.5 billion years from now. At this point, our Sun will exhaust the hydrogen fuel in its core and begin burning hydrogen in a shell around the core. This marks the beginning of the Sun's red giant phase, a dramatic transformation where our star will expand to hundreds of times its current size. As the Sun expands into a red giant, it will likely engulf the orbits of Mercury and Venus. Whether Earth will be swallowed remains uncertain and depends on complex interactions between the Sun's expansion and mass loss, which alters orbital dynamics. Some models suggest Earth might narrowly escape direct engulfment, but would nevertheless be subjected to temperatures high enough to melt its surface into a magma ocean. Other models predict Earth will indeed be consumed by the expanding Sun. Even if Earth physically survives as a planetary body, it would be transformed beyond recognition, a barren, scorched world bearing no resemblance to the life-supporting planet we inhabit today. Any life that managed to persist through the earlier phase of ocean loss would almost certainly be eradicated during this red giant expansion. It's worth noting that during all these solar system changes, the ongoing collision between our galaxy and Andromeda would provide a spectacular astronomical show, assuming any observers remained to witness it. During the first close passage, Andromeda would appear as an enormous structure dominating Earth's night sky, far larger and brighter than any celestial object visible today except the Sun and Moon. The previously diffuse, barely visible smudge would transform into a magnificent spiral filling a significant portion of the sky, its spiral arms and bright star-forming regions clearly visible to the naked eye. As the galaxies began to distort from their mutual gravitational attraction, enormous arcs of stars would stretch across the sky, creating new, temporary constellations unlike anything in our current night sky. The areas where the galaxies overlap would shine brightly with new star formation, creating blue-white patches similar to the star-forming regions we now observe in distant colliding galaxies. During the hundreds of millions of years between encounters, the distorted structures of both galaxies would slowly rotate and evolve in Earth's sky, creating an ever-changing cosmic panorama. With each successive passage, the orderly spiral structures would become increasingly disrupted, eventually transforming into the chaotic streams and shells characteristic of merging galaxies. For any human descendants or post-human intelligence still existing during this period, survival would depend on having developed the technology for interstellar migration. The challenges facing life on Earth from our own star's evolution would necessitate relocation to other star systems long before the galactic merger itself posed any issues. Indeed, the collision between galaxies might offer new opportunities, as gravitational interactions could potentially make certain star systems more accessible by altering their trajectories. An advanced civilization might take advantage of the merger to explore newly accessible regions of both galaxies. The enhanced star formation triggered by the collision would create many new stellar systems, some potentially suitable for colonization. The very process that ends the separate existence of our two spiral galaxies could, paradoxically, enable the expansion of any surviving technological civilizations. Of course, this assumes that humanity or its descendants survive the next few billion years, an extraordinary time span considering our species has existed for only about 300,000 years, and our technological civilization for mere thousands. The obstacles to such long-term survival are immense and extend far beyond the astronomical changes described here. Social, technological, and evolutionary changes over such timescales are virtually impossible to predict. By the time the merger completes and Andromeda fully forms as an elliptical galaxy some 7 billion years from now, it's almost certain that Earth will no longer exist as a habitable world. The Sun will have progressed through its red giant phase and eventually shed its outer layers, leaving behind only a cooling white dwarf star, the dense core of our once vital Sun, gradually radiating away its remaining heat over trillions of years. The very concept of Earth experiencing the Andromeda Milky Way collision raises profound questions about time, existence, and our cosmic perspective. When we consider events billions of years in the future, time frames orders of magnitude longer than human civilization or even our species has existed, we confront the immense scales that characterize our universe and the relatively brief moment our lives occupy within cosmic history. The collision between Andromeda and our Milky Way represents one of the most dramatic events in our local cosmic neighborhood. Yet it unfolds over timescales so vast they challenge human comprehension. While we can mathematically model and predict this future merger, the billions of years involved represent a duration approximately 500,000 times longer than recorded human history. This extreme timescale forces us to consider the temporary nature of everything we typically regard as permanent. When astronomers first determined that Andromeda is on a collision course with our galaxy, it transformed our understanding of galactic evolution, rather than seeing galaxies as static, unchanging islands of stars. We now recognize them as dynamic systems that grow, interact, dot, and merge over cosmic time. This perspective shift mirrors historical changes in human thinking, from viewing Earth and solar system as fixed and eternal to recognizing them as evolving systems with finite lifespans. The collision reminds us that change is fundamental to cosmic existence. The galaxies we observe today, including our home Milky Way and neighbouring Andromeda, represent merely the current arrangement of matter in an ongoing process of reorganisation that began with the Big Bang and will continue long after these particular structures have ceased to exist as separate entities. The stars, planets, and even atoms that compose our bodies have been and will be rearranged countless times throughout cosmic history. Despite the cataclysmic scale of a galactic collision, it's remarkable that individual solar systems within the merging galaxies will likely remain largely intact. The vast distances between stars mean that direct stellar collisions will be extraordinarily rare. This illustrates an important principle of structure at different scales. Chaos at one level, the galactic structure, can coexist with stability at another level, individual solar systems. This multi-scale perspective provides a useful framework for understanding many natural systems, from galaxies down to ecological communities. The eventual fate of our galaxy also raises questions about longevity and legacy. Human civilizations throughout history have constructed monuments and created works intended to preserve their memory for future generations. Yet even the most enduring human structures, the pyramids of Egypt, the Great Wall of China, have existed for only a few thousand years, a mere instant compared to astronomical timescales. When we contemplate events billions of years in the future, conventional notions of legacy and remembrance seem almost meaningless. For any technological civilization, the knowledge of inevitable stellar and galactic transformations necessitates long-term planning beyond a single planet or even a single star system. The changes our sun will undergo, independent of any galactic collision, make Earth uninhabitable within a few billion years. Any truly long-lived civilization would need to develop the capability for interstellar migration simply to survive the natural evolution of its home star. The collision also highlights questions about cosmic uniqueness and commonality. Throughout the universe, galaxy mergers occur regularly. We observe them at various stages in distant systems. What feels unique and personally significant to us, the future of our home galaxy, is actually a common process in cosmic evolution. This tension between personal significance and cosmic commonality appears throughout human engagement with astronomy. From early religious interpretations of celestial events to modern scientific understanding. Perhaps most fundamentally, contemplating events billions of years in the future reminds us of the limitations of human foresight. Our most sophisticated scientific models can predict the gravitational dance of galaxies far into the future, yet we struggle to accurately forecast Earth's climate a century ahead or social changes over mere decades. This contrast between astronomical predictability and earthly uncertainty stems partly from the simplicity of gravitational physics compared to the complexity of biological and social systems. Despite these limitations, the human ability to conceptualize and model events billions of years in the future represents an extraordinary cognitive achievement. Through mathematics, physics, and astronomy, we transcend the narrow time frame of our individual lives to comprehend processes unfolding over billions of years. This cognitive time travel, projecting our understanding beyond our direct experience, distinguishes human intelligence and underlies much of our scientific progress. When we observe Andromeda today through telescopes or even with the naked eye under dark skies, we're not just seeing another galaxy, we're seeing our own cosmic future. The light that reaches us began its journey 2.5 million years ago, but the object itself represents what will combine with our galaxy billions of years from now. This connection across vast distances of both space and time gives Andromeda a unique significance among all celestial objects visible from Earth. The Andromeda-Milky Way collision reminds us that even the largest structures we observe, entire galaxies containing hundreds of billions of stars, are themselves temporary arrangements in an ever-changing universe. Like individual lives, species, planets, and stars, galaxies too have finite lifespans as discrete entities. They form, evolve, interact, merge, and eventually transform into new structures. This universal impermanence operates across all scales of cosmic organization, from the smallest particles to the largest structures in the observable universe. In this context, the future merger doesn't represent an ending so much as a transition, two spiral galaxies becoming one elliptical galaxy, with different characteristics but containing the same stars, planets, and potential for life. The matter and energy will remain, rearranged into new forms. This pattern of transformation without true destruction or creation mirrors processes we observe throughout nature, from ecosystems to chemical reactions, suggesting a fundamental continuity underlying change at all scales.